What if your entire life, every laugh, every tear, every single Tuesday, from your first breath to your last already exists? Not as a memory or some far-off possibility, but as a complete, finished reality. What if you could step outside the river of time and see your whole life at once? A vast, frozen sculpture of your existence. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This isn't the plot of a science fiction novel. This is the bizarre and profound reality suggested by more than a century of physics. It tells us the past, present, and future aren't just moments that come and go. Instead, they're all equally real, coexisting in a single, unified block of spacetime. Today, we're heading to the razor-thin boundary between the time we feel and the timelessness that physics describes. We'll start with our comfortable, common-sense intuition of time as an arrow flying forward. Then, we're going to let Albert Einstein shatter that intuition. We'll look at the undeniable proof that this isn't just a wild theory, but a measurable fact of our universe. And finally, we'll stand at that mind-bending boundary and face the deepest questions this reality throws at us. Questions about free will, destiny, and the nature of consciousness itself. By the end, the simple ticking of a clock might never sound the same to you again. The comforting lie. Time as a river. Before we jump into the deep end, let's start on solid ground. Our own experience. How do you feel time? For pretty much everyone who's ever lived, the answer is the same. Time flows. It's a powerful, unstoppable river, carrying us from a fixed past toward an open future. This moment right now feels special. It feels like the cutting edge of reality, the only point that's truly real. The past is a gallery of ghosts, memories that are gone forever. The future is a fog of possibility, unwritten and unformed. This intuitive view actually has a name. It's called asterisk presentism. It's the simple, common-sense idea that only the present truly exists. The Roman Empire? It was real, but it isn't anymore. Your great-grandchildren? They will be real, but they aren't yet. According to this view, the only thing that objectively exists is what's happening in this fleeting moment. This feeling is so deep in our bones it feels less like a belief and more like a law of nature. Our languages are built around it with past, present, and future tenses. Our emotions are governed by it. We feel regret for a past we can't change and hope for a future we can't see. The flow of time is the soundtrack to our lives. Evolutionarily, this makes total sense. To survive, you need to get your head around cause and effect. A predator has to learn from the hunt that just happened, the past, to guess its prey's next move, the future, in the critical moment of now. Our brains are storytelling machines, and they always tell the story in a straight line, stitching moments together into a coherent arrow of time. We feel like we're moving through time because our consciousness is constantly updating its model of the world. The philosopher Arthur Pryor was a big champion of presentism. He argued that statements about the past and future are only true because of how they relate to the present. The statement, "Dinosaurs roamed the earth," is true now because it refers to something that was, at one point, present. But the dinosaurs themselves? A strict presentist would say they simply don't exist anymore. They're unreal. This is the model of time that just feels right. It's comfortable. It's the world of our personal experience. But in the early 20th century, a patent clerk in Bern, Switzerland, published a paper that took a sledgehammer to this entire picture. His name was Albert Einstein, and his theories of relativity didn't just tweak our understanding of time, they revealed that our most fundamental intuition about its flow might be a profound and persistent illusion. The crack in reality. Einstein's revolution. To see how our intuition breaks down, we have to look at an idea at the heart of Einstein's special theory of relativity. The asterisk relativity of simultaneity. It sounds complex, but it's the one thing that completely dismantles the idea of a universal now. It proves that two people can disagree on whether two things happened at the same time, and both can be right. Let's use a thought experiment Einstein loved. Picture a long train moving at a very high speed. In the exact middle of a carriage sits Priya. On a railway platform, watching the train go by, stands Amit. Now, imagine that at the exact moment Priya and Amit are lined up, two bolts of lightning strike the train. One hits the very front of the carriage, and the other hits the very back. From Amit's perspective on the platform, it's simple. He's standing exactly halfway between the two strikes. Since the light from both flashes travels at the same speed and covers the same distance to reach his eyes, the light arrives at the exact same moment. Amit sees the two events as perfectly simultaneous. He'd say, the lightning bolts struck at the same time. But what does Priya see? She's on the moving train. As the light from the strikes travels toward her, she is rushing towards the flash from the front and away from the flash from the back. This means the light from the front of the train has less distance to cover to reach her. Because of this, Priya will see the flash from the front of the train before she sees the flash from the back. And since she knows she's in the middle of the carriage and that the speed of light is constant, she can only come to one conclusion. The lightning must have struck the front first. For her, the events were not simultaneous. So, who is right? Amit, who says they happened at the same time? Or Priya, who says the front strike happened first? Einstein's revolutionary answer is that they are both right. There is no universal now. Amit's now includes both lightning strikes happening at once. Priya's now, at that same instant, is different. Her slice of time is tilted relative to Amit's. What counts as a single moment depends entirely on how you're moving. This isn't just a trick of perception. It's a fundamental feature of the fabric of reality, which Einstein called spacetime. He realized space and time are woven together into a single, four-dimensional continuum. Your motion through space literally affects your passage through time. And this is where it gets really weird. If there is no universal now, then the idea that the present is uniquely real completely falls apart. My now could contain an event that is in your future. Your now could contain an event that is in my past. Imagine a third observer, Maria, flying in a spaceship in the opposite direction. For her, the situation would be flipped. She'd see the lightning strike the asterisk back of the train first. So now we have three people, all making perfectly valid measurements, who completely disagree on the order of events. If the order of events can be different for different people, it suggests that past, present, and future aren't fixed categories. They're more like directions, such as left, right, up, and down. What's left for me is right for someone facing me. And what's future for me could be present for someone moving relative to me. This realization tears a crack in our intuitive picture of time and forces us to consider a much stranger alternative. The block universe revealed. If the past, present, and future aren't what we thought they were, then what is the true nature of reality? The answer that comes out of relativity is a concept called the asterisk block universe. This view, also known as asterisk eternalism asterisk, suggests that all of time every moment from the Big Bang to the very end exists at once. The universe is a giant, four-dimensional block of spacetime, containing every event that has ever happened or ever will happen. The easiest way to picture this is to think of spacetime as a loaf of bread. The entire loaf is the whole history of the cosmos. A single slice of that loaf is the universe at one particular moment, a 3D snapshot of all of space. Your birth is a slice near one end. Your death is a slice further down. This very moment, as you're taking this in, is just another slice somewhere in the middle. In the block universe, all these slices are equally real and already exist. The dinosaurs, your childhood, and the 22nd century are just different locations within this 4D block. The passage of time we feel is an illusion. There's no special now moving through the loaf. Our consciousness simply experiences these slices one after another, creating the feeling of flow. This is where the relativity of simultaneity clicks into place. Remember Amit and Priya? In the loaf of bread analogy, they're just slicing the block at different angles. Amit, standing still on the ground, takes a straight, perpendicular slice. In his slice, both lightning strikes happen in the same moment. Priya, because she's moving, slices the loaf at an angle. Her slice of now is a tilted cross-section of the block. For her, that angled slice cuts through spacetime in a way that it includes the front lightning strike, but does not yet include the rear one. That event lies in what she would call her future. This is the core of the block universe. There's no privileged now. Since all these different slices are equally valid, it means all the moments they slice through must be equally real. The future is no less real than the past. They're all just different locations in spacetime. Think of it like a movie on a Blu-ray disc. The entire film beginning, middle, and end exists on the disc all at once. But when you play it, you only experience it one frame at a time, creating the illusion of a story unfolding. Our consciousness is like the laser reading the disc. It illuminates one frame of spacetime at a time, giving us the powerful experience of time passing. But the whole movie of our life is already there. This view is sometimes called the B-theory of time. While philosophers debate the details, many physicists agree that the block universe is the model that fits best with Einstein's relativity. It paints a picture of a static universe where when is just another coordinate, like where your birth isn't gone, it's just located at a different temporal coordinate. The undeniable evidence. Okay, this idea of a block universe can sound like a wild, late-night philosophical debate. It's easy to dismiss it as a mathematical curiosity. But it's not. The physical effects that lead to this conclusion are measured every single day, and the technology you use right now relies on them being true. The most powerful example is the Global Positioning System, GPS, The GPS in your phone works by talking to satellites orbiting the Earth, each carrying an incredibly precise atomic clock. By calculating the tiny differences in the arrival times of signals from at least 4 satellites, your phone can pinpoint your location on the planet. The whole system depends on near-perfect timing. An error of just a few billionths of a second can throw your location off by several feet. And this is where Einstein is non-negotiable. First, the satellites are moving incredibly fast, about 14,000 kilometers per hour. Special relativity says that moving clocks tick slower. Because of their speed, the satellite clocks slow down by about 7 microseconds every day compared to clocks on Earth. Second, the satellites are orbiting high above the surface, where gravity is weaker. General relativity says that clocks in weaker gravity tick faster. This effect speeds their clocks up by about 45 microseconds a day. Combine the two, and the clocks on GPS satellites run faster than clocks on the ground by about 38 microseconds every single day. If engineers didn't correct for this, your GPS would accumulate errors, making it useless in hours. After just one day, it would misreport your position by over 10 kilometers. Your GPS works because it's programmed to account for the fact that time is literally passing at a different rate in orbit. This is direct proof that time isn't absolute. Another stunning piece of evidence comes from the muon experiment. Muons are unstable particles created when cosmic rays hit our upper atmosphere. They have a very short lifespan, about 2 microseconds. Even traveling near the speed of light, simple math says most muons should decay long before they reach the Earth's surface. And yet, we detect tons of them down here at sea level. Why? Time dilation. From our perspective, the muons are moving so fast that their internal clocks slow down dramatically. While a muon at rest would decay in 2 microseconds, its lifetime gets stretched when it's moving that fast. From our point of view, their time slows down, allowing them to survive the long journey to the surface. This isn't a guess, it's been measured with incredible precision for decades. These experiments all confirm the same bizarre truth. Time is relative. The rate at which time passes is not a universal constant. And if the rate of time can change, our intuitive idea of a single, flowing river of time is fundamentally broken, pushing us toward the strange, static reality of the block universe. The philosophical fallout. Life in a frozen universe. Accepting the block universe isn't just a fun intellectual puzzle. It has profound, and for many people, deeply unsettling consequences for how we see our lives, our choices, and our very selves. The first, and most jarring, is free will. If the future already exists in the block, just like the past, then it seems like all our future actions are already written. The choice you think you're about to make, what to eat for dinner, who to call, whether to keep watching, isn't a choice between open possibilities. It's just you arriving at the moment in space-time where that choice is already recorded. This is fatalism. The idea that the future is as fixed as the past. From this perspective, our feeling of freedom is the most powerful illusion we have. But it's not so simple. Many philosophers, called compatibilists argue that free will and a block universe can get along just fine. They suggest that free will doesn't mean you can change the future. It just means your choices come from your own internal desires and deliberations, without someone forcing your hand. Even if your decision is a fixed point in space-time, it is your decision that makes it so. The future exists in the block because of what you will choose to do. You can't change the future, but you are a vital part of what creates it. Then there's the question of consciousness. What are we in this block? A popular metaphor is the spotlight. Imagine your life as a long, 4D, world line, snaking through space-time. Your consciousness is a spotlight moving along that line, illuminating one moment at a time. This explains why we feel time flow and why we only experience the present. But what is this spotlight? What makes it move? And why only from past to future? Physics has no answer. The mystery of time seems to be tangled up with the mystery of consciousness itself. Perhaps the most human implication of the block universe comes when we think about loss and mortality. In our normal view of time, when someone we love dies, they're gone forever. That sense of absolute loss is the source of our deepest grief. But in the block universe, no one is ever truly gone. Their entire life remains a permanent, real part of the space-time block. They're just at a different location in time. Your last conversation with them isn't a ghost in your memory. It's a real place in space-time that exists just as concretely as the room you're in now. This was exactly what Einstein meant in his most moving words on the subject. When his lifelong friend Michel Besso died in 1955, Einstein wrote a letter to Besso's family, saying, "Now he has departed from this strange world a little ahead of me. That means nothing. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." This wasn't just a nice sentiment. For Einstein, it was a statement of physical reality. Besso wasn't gone. He was just located at a different point in time. This view can offer a strange kind of comfort. It suggests that the people and moments we cherish are never lost, but are preserved forever in the timeless sculpture of space-time. Finally, when we get to the absolute frontiers of physics, things get even weirder. The Wheeler-DeWitt equation asterisk, an early attempt to merge Einstein's relativity with quantum mechanics, has a stunning result. The variable for time vanishes completely from the equation. It describes a static, timeless quantum state of the entire universe. This has led to what physicists call the problem of time. If the universe is fundamentally timeless, where does the time we experience come from? The leading idea is that time isn't fundamental at all. It's an emergent property, something that arises from a more basic, timeless reality, much like heat emerges from the motion of atoms. We started this journey with the familiar feeling of time as a flowing river. But we followed the path Einstein laid out and watched that intuition shatter against the hard facts of physics. The relativity of simultaneity broke the idea of a universal now, and the daily proof from GPS satellites and cosmic particles confirmed that time's passage isn't absolute. This led us to the staggering vision of the block universe, a static, four-dimensional reality where past, present, and future are all equally real, coexisting like places on a map. Our lives aren't unfolding stories but completed sculptures, and our consciousness is moving along a pre-existing path, experiencing one frozen moment at a time. Standing at this boundary between our feeling of time and the timelessness of physics forces us to confront the biggest questions there are. It challenges our ideas of free will, changes how we think about life and death, and ties the enigma of time to the enigma of consciousness itself. It suggests that the flow of time, the most fundamental experience we have, might just be a grand illusion. In the end, we are left with the haunting and beautiful words Einstein wrote to his friend's grieving family, a truth from physics offered as a comfort. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. Science just found a place where time doesn't exist. What if I told you there's a place where the entire history of the universe, from the Big Bang to its very end, all happens in an instant? A place where time, as we know it, just doesn't exist. And the craziest part? Science says this place is real, and it's all around us. It's not hidden in some far-flung corner of the cosmos or locked away behind a black hole. It's right here, woven into the very fabric of light itself. This isn't science fiction. This is a trip to the absolute limit of reality, into a dimension without a clock, a place that could rewrite everything we think we know about existence. And to get there, we don't need a spaceship. We just need to understand what it really means to travel at the speed of light. The normal world. For all of us, time is the most fundamental part of reality. It's the silent metronome dictating the rhythm of our lives, that steady, forward march from birth, to life, to whatever comes next. We feel it in our own heartbeat, see it in the turning of the seasons, in the slow erosion of a mountain, and the quick bloom of a flower. Our whole language is built around it. Yesterday, today, tomorrow. Our memories are in the past, our hopes are in the future. We experience time as a giant river, flowing in one direction, carrying everything and everyone along with it. This intuitive feeling was first written into the laws of physics by Sir Isaac Newton. For him, time was absolute. It was a single, cosmic clock that ticked at the exact same rate for everyone, everywhere. Whether you were sitting on a park bench or on a planet in a distant galaxy, Newton believed that 1 second for you was 1 second for all. It was simple, elegant, and for over 200 years, it was the bedrock of physics. We built our world on this idea. The gears of the Industrial Revolution, train schedules, the whole concept of a synchronized global society, it all rested on the idea of a single, shared time. But that comforting, orderly picture of reality was about to be completely shattered. At the dawn of the 20th century, a young patent clerk in Bern, Switzerland, asked a question so profound it would crack the very foundations of existence. His name was Albert Einstein, and his work would reveal that the river of time wasn't a steady current, but a strange, flexible, and deeply personal experience. He showed us that the ticking of a clock depends on how you move and where you are. And in doing so, he accidentally pointed the way to a place where the clock doesn't tick at all. The first crack in reality. The revolution didn't start with a huge experiment, but with a simple thought. A thought experiment. Einstein imagined what it would be like to ride alongside a beam of light. If you could somehow match its incredible speed, what would you see? Would the light wave look like it was frozen next to you, a stationary, shimmering ripple? This simple question had huge, contradictory implications for the laws of physics, especially the ones that said the speed of light in a vacuum is a universal constant. It should be the same for every single person, no matter how they're moving. This was a major paradox. Think about it. If you're driving on the highway at 60 miles per hour and the car next to you is also doing 60, it looks like it's not moving relative to you. But the laws of physics insisted light doesn't play by those rules. No matter how fast you chase it, you'll always measure it zooming away from you at the same mind-boggling speed. About 300,000 kilometers, or 186,000 miles, per second. This one stubborn fact forced Einstein to a radical conclusion. If the speed of light is constant for everyone, then something else has to change to make the math work. That something else, he realized, had to be space and time itself. He called this new framework special relativity, and it turned the Newtonian world completely upside down. To get how this works, let's use one of the most famous thought experiments ever: the light clock. Imagine a clock that measures time by bouncing a single particle of light, a photon, between two mirrors. Let's say the mirrors are 300,000 kilometers apart. The photon zips from the bottom mirror to the top and back down. Each round trip takes exactly 2 seconds. Tick, tock. 1 second up, 1 second down. For you, standing right next to this clock, it works perfectly. Now, let's put that same clock on a spaceship moving incredibly fast, say, half the speed of light, and you watch it fly by. From your perspective on the ground, as the clock moves, the photon isn't just traveling up and down anymore. It's also moving forward with the ship. So instead of a straight vertical line, the photon now has to travel a longer, diagonal path. And this is where it gets weird. That diagonal path is longer than the straight vertical one. But remember the cornerstone of Einstein's theory. The speed of light must be constant for everybody. So the photon on the moving ship is traveling at the exact same speed as the photon in your stationary clock. Since it has to travel a longer distance, but its speed can't change, there's only one possible conclusion. It must take more time to complete its journey. From your perspective on the platform, the moving clock is ticking slower. The tick that took 1 second on your clock now takes longer on the ship's clock. This isn't a mechanical glitch or an illusion. Time itself is genuinely passing more slowly for the moving clock. This effect is called time dilation. And it's not just a theory, it's a proven fact. Atomic clocks on GPS satellites run at a slightly different rate than clocks on Earth and have to be constantly corrected. If they weren't, the whole system would be useless within hours. Scientists have also flown hyper-accurate atomic clocks on jets and found they fell behind the clocks on the ground by tiny fractions of a second, exactly as Einstein predicted. This was the first crack in our reality. Time wasn't a rigid ruler. It was a flexible fabric, and motion could stretch it. But if time slows down when you move, what happens when you push that motion to the absolute, cosmic limit? What happens when you approach the speed of light? The journey to the edge. Einstein's discovery of time dilation wasn't just some minor tweak. It was a doorway to a whole new reality. The math of special relativity showed a bizarre relationship between speed and time. The faster you move through space, the slower you move through time. This isn't something you notice in daily life. The speeds we experience in a car, on a plane, even orbiting the Earth are practically zero compared to the speed of light. The time dilation effect is so tiny it's impossible to measure without atomic clocks. But as you start to get close to light speed, the effect becomes dramatic. Imagine you're on a spaceship heading to our nearest neighboring star system, Alpha Centauri, about 3 light years away. You leave your twin behind on Earth. Let's say you travel at 50% of the speed of light. For your twin on Earth, the round trip takes about 6 years. But for you on the ship, time is moving slower. According to your clocks, the journey only takes you about 5 years. You get back to Earth having aged about 2 years less than your twin. A cool party trick, but not yet reality-shattering. Now let's ramp it up. You take the same trip, but your ship hits 90% of the speed of light. For your twin, the trip now takes a little over 7 years. But for you, time has slowed way down. Your journey takes you only about 2 years. You come home to find your twin is almost 3 years older than you. Let's push it even further. You accelerate to 99% of the speed of light. The trip for your twin on Earth takes about 34 years. For you, it's just 4 months. You barely have time to watch a full season of a TV show, and when you get back, your twin has aged years while you've only aged months. But what if we could push it to the absolute limit? Your incredible spaceship accelerates to 9,999% of the speed of light. From your twin's perspective, the journey to Alpha Centauri is still just over 3 years long. But for you, time has slowed to a crawl. The entire 3 light-year journey would flash by in just over a day and a half. You could fly to a star and back in under a week, but when you landed, everyone you ever knew would be nearly a decade older. This is the famous twin paradox, and it shows the mind-bending power of time dilation. The faster you go through space, the slower you go through time. As your speed gets closer and closer to the speed of light, the time dilation effect approaches infinity. A journey that an outside observer sees as taking millions of years could pass for you in seconds. You are essentially fast-forwarding through the universe's timeline. This isn't just a math trick. It's real. Experiments in particle accelerators prove it every day. Unstable particles like muons, which normally decay in a fraction of a second, survive much longer when sped up to near light speed because their internal clocks are ticking slower. In fact, we see this with muons created by cosmic rays in our own atmosphere. They shouldn't have enough time to reach the Earth's surface before decaying, but they do, because from our point of view, their time has been stretched, extending their lives. So, we're standing at the edge of familiar reality. We've seen that time isn't constant, it can be stretched and slowed by speed. This leads to the ultimate question. We've seen what happens as you get closer to the speed of light. But what happens if you actually reach it? What happens when you finally catch that beam of light from Einstein's imagination? The answer is where things get truly strange, because at this ultimate speed limit, we find a place where time ceases to exist. The destination. The photon's perspective. So far, we've been the observer, watching from the outside as time slows down for someone else. We've been the twin on Earth or the scientist in the lab. Now, we have to take the final leap. We have to become the thing that travels at the speed of light. We have to become the photon. A photon is a particle of light. By its very nature, it's born traveling at the speed of light, and it will die traveling at the speed of light. It has no other speed. It lives at the universe's ultimate speed limit. So, what is the universe like from a photon's point of view? The equations of special relativity give a clear and staggering answer. For anything with mass, time slows down as it approaches light speed. But for a massless particle like a photon that travels at light speed, the time dilation factor becomes infinite. This means that, from the photon's perspective, time does not pass at all. Let that sink in. It's not that time moves really, really slowly. It's that it stops completely. For a photon, there is no such thing as duration. There's no ticking clock, no before and after. There is only a single, frozen, timeless instant. Imagine a photon that was emitted from a star in the Andromeda galaxy, 5 million light-years away. From our perspective here on Earth, that little particle of light takes an epic journey across the vast emptiness of space. It travels for 5 million years, witnessing the birth and death of stars and the slow dance of galaxies. But from the photon's perspective, none of that happened. For the photon, the moment it was emitted in Andromeda and the moment it was absorbed by your eye are the same moment. The entire 5 million year journey across the cosmos happened in zero time. The start and end of its trip are simultaneous. And it's not just time that gets warped. Space does, too. Special relativity tells us that as an object approaches light speed, the universe in its direction of travel shrinks. This is called length contraction. At the speed of light, this contraction becomes absolute. The distance between any 2 points in its direction of travel collapses to zero. So for our photon traveling from Andromeda, the 5 million light-years of distance simply vanish. The entire universe, in its direction of travel, flattens into a single point. This is the place where time doesn't exist. It is the reference frame of light itself. In this frame, the universe has no duration and no distance. The Big Bang and the eventual death of the cosmos could be simultaneous events. A journey from one end of the universe to the other is an instantaneous leap. The physicist Julian Barber calls this timeless state a collection of nows, suggesting reality is just a vast pile of static, individual moments, like frames of a cosmic film. For us, time emerges as we perceive a sequence of these frames. But for a photon, there is no sequence. There is only one frame, one eternal now, that contains its entire existence. And this isn't some hypothetical realm. It's a fundamental part of our reality. Every time sunlight warms your face, every time you look at the stars, you are interacting with particles that have just completed an instantaneous journey from a timeless dimension. They are messengers from a place without a clock. So what? The idea that there's a reference frame where time doesn't exist is more than just a cool piece of trivia. It hits at the heart of our biggest questions. What is time? Is it a real, flowing river, or is it an illusion? The photon's timeless existence suggests our perception of time might not be as fundamental as we think. It hints that time could be an emergent property, something that arises from our specific, slow-moving, mass-based point of view, rather than being an absolute feature of the universe. This isn't a new idea. Over 500 years ago, the Greek philosopher Antiphon argued that time was a concept, not a real substance, a tool our minds use to order events. Later, Parmenides argued for a static, unchanging reality where past, present, and future all exist simultaneously, and our sense of flow is the illusion. These ancient ideas find a startling echo in modern physics. The block universe theory, a natural consequence of relativity, portrays all of spacetime as a static, four-dimensional block where every event past, present, and future already has a fixed coordinate. The now is just the slice of this block we happen to be experiencing. Our feeling of time passing is like a spotlight moving along a finished roll of film. The whole movie is already there. Our consciousness just illuminates it frame by frame. Even Einstein was bothered by this. He famously wrote to a friend, "People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion." This puzzle gets even deeper when physicists try to unite Einstein's theory of gravity with quantum mechanics. This search for a theory of everything leads to what's known as the asterisk problem of time. The master equation that attempts to describe the entire universe, the Wheeler-DeWitt equation, has a shocking feature. The variable for time, t, is completely missing. It describes a static, frozen, timeless universe. This has led some physicists to propose that time emerges from deeper quantum processes. For instance, recent studies are exploring the deep connection between time and quantum entanglement, suggesting that the way a quantum system experiences time might depend on its entanglement with another system that acts as a clock. For a lonely, isolated system that isn't entangled with a clock, time might not happen at all. So, the photon's perspective isn't just a weird outlier. It's a profound clue that the universe allows for a state of being where time is meaningless. It forces us to wonder if we aren't passengers on a flowing river, but observers of a static landscape, our experience of a journey created by the limits of our own perception. The clock on your wall may be telling you the time, but the light from that clock is telling you that time itself may be the greatest illusion of all. Beyond the photon, the timelessness of a photon is our clearest window into this strange reality, but it's not the only one. Physics points to other, even more extreme places where time shatters. The most famous are black holes. A black hole is an object with gravity so intense that nothing, not even light, can escape once it crosses the event horizon. According to Einstein's general relativity, massive objects warp spacetime, and this warping slows down time. This is called gravitational time dilation. It's been proven. A clock on the floor ticks microscopically slower than a clock on a table because it's closer to Earth's mass. A black hole is the most extreme version of this. As you get closer and closer to a black hole's event horizon, an outside observer would see your clock ticking slower and slower until, at the horizon, it would appear to stop completely. From the outside, you would seem frozen in time for eternity. The event horizon is a place where, for any object falling in, time effectively ends. What happens after you cross that line is where the known laws of physics break down. Inside the black hole, some theories suggest space and time might even swap roles. The event horizon is a frontier between our world of ticking clocks and a region where time behaves in a way we can't fully grasp. But the riddles of time don't just exist on a cosmic scale. They pop up in the bizarre world of quantum mechanics. And then there's the quantum world's own brand of weirdness, quantum entanglement. Einstein called it spooky action at a distance. When two particles become entangled, their fates are linked, no matter how far apart they are. If you measure a property of one particle, you instantly know the corresponding property of the other, even if it's on the opposite side of the galaxy. This connection appears to be instantaneous, seemingly breaking the cosmic speed limit. While it doesn't let you send messages faster than light, it does suggest a kind of timeless connection that operates outside our normal rules of spacetime. It's like a glimpse into a temporal web connecting everything. From the speed of light journey of a photon, to the time-stopping horizon of a black hole, to the spooky connection of entangled particles, physics is littered with clues. They all point in the same direction. Our everyday experience of a smooth, forward-flowing time is probably an illusion. A useful, powerful illusion, but an illusion nonetheless. The philosophical frontier. To say that time might not be fundamental is to open a philosophical Pandora's box. It forces us to rethink what it means to exist, to change, and to cause things to happen. First, the big paradox. If time doesn't pass, how can anything change? We see change everywhere. How does a static universe account for this? Proponents of a timeless universe, like Julian Barber, use a great analogy, a flipbook. The entire story, every scene, every action already exists on the individual static frames. Change is the illusion you get by viewing those frames in sequence. Barber argues the universe is a collection of these static nows. We don't move through time. Instead, our consciousness experiences a succession of these nows, and because each one contains records of the previous ones like memories in our brain or fossils in the ground, we create the illusion of a past. This leads to the next question. Can something even exist without a before and after? Our gut reaction is no. Existence seems to imply lasting for some amount of time. Yet, timeless theorists argue that existence is about configuration, not duration. A triangle exists because of the relationship between its 3 points, not because it lasts for 5 seconds. In the same way, the universe could just be a vast set of relationships, existing as a single, timeless mathematical object. Of course, this idea has its own problems. If reality is timeless, why does the illusion of time emerge so consistently for us? What determines the sequence of nows that we experience? And what about the arrow of time? The fact that we remember the past but not the future. And how can we talk about cause and effect? If A causes B, doesn't A have to happen before B? If all moments exist at once, then causality isn't about time, but about logic. The pattern of the universe is just structured so that a state we call broken egg is always found near a state we call egg falling. We're left standing on a razor's edge. On one side is our gut feeling of a world in constant motion, ruled by the clock. On the other is the picture painted by our best theories of physics. A static, timeless, interconnected reality. Things that move slowly, like us, live deep in the world of time. Things that move at the universe's ultimate speed limit, like photons, inhabit a world of timelessness. And things like black holes mark the border where one reality seems to bleed into the other. We started with a simple question. What happens at the speed of light? We journeyed from the clockwork universe of Newton, through the elastic spacetime of Einstein, and arrived at the perspective of a photon, a place of absolute stillness, and eternal now, where a billion-year journey is the same as the blink of an eye. We saw this isn't just some weird glitch. It's a clue, echoed by black holes and quantum entanglement. It's a signpost pointing toward a radical new view of reality, one where time itself may be a grand illusion, an experience that arises from our limited, slow-moving perspective within a vast, static, and timeless cosmic structure. The idea that the universe, at its deepest level, is frozen is a tough one to swallow. It goes against every instinct we have. Yet, this is where the science points. It suggests that timelessness isn't nothingness. It's the canvas upon which the illusion of time is painted. The now you are experiencing as you watch this might be just one frame in an infinite cosmic film. This doesn't make our experience cheap. It makes it all the more mysterious. It means the feeling of moving from a known past into an unknown future could be the most beautiful story our universe tells itself, through us. So the next time you look up at the night sky, at the ancient light from a distant star, remember the journey that light took. A journey of millions of years for us, but for it, an instantaneous leap. It's a reminder that woven into the fabric of our universe is a dimension without a clock, a secret that whispers to us in every single beam of light. What do you think? Does it change how you see things, to think that the flow of time might be an illusion? Let us know your thoughts in the comments. And if you want to keep questioning the fundamental nature of reality with us, make sure you subscribe. The universe is full of secrets, and our journey to uncover them has only just begun. Why time only moves in one direction? Think about this. You can scramble an egg, but you can't unscramble it. You can shatter a glass, but you can't unshatter it. A building can collapse into rubble, but rubble will never spontaneously build itself into a skyscraper. This simple, one-way street of reality is so fundamental to how we experience the world, we barely even notice it. It's just how things work. The past is done. The future is up for grabs. But this everyday truth hides one of the biggest, most profound mysteries in all of science. It's a puzzle that links a cracked egg on your kitchen counter to the birth of the entire universe, and even to its ultimate, desolate end. Because buried in that irreversible act is the answer to the question: why does time only move in one direction? Why are we all on this relentless, one-way trip from past to future? Why is there an arrow of time at all? The answer is both beautifully simple and cosmically huge. It's a universal law of growing chaos called entropy, and it's the reason time is locked on a one-way street. But to get it, we first have to understand a strange and counterintuitive truth. On the most basic level, the laws of physics that run our universe don't actually care about the direction of time. And here's where it gets really weird. If you could zoom in past the egg, past the molecules, all the way down to the individual atoms and the forces that govern them, you'd find something shocking. The fundamental laws of physics running the show, gravity, electromagnetism, the weird rules of quantum mechanics, almost all of them work perfectly whether you run the clock forwards or backwards. So, if the bedrock laws of reality have no preference for past or future, where does this unbreakable arrow of time actually come from? The search for that answer doesn't begin in a physics lab, but with steam engines. The mystery deepens: physics without a past or future. We like to think of the laws of physics as solid, dependable, absolute. Newton's laws of motion are a perfect example. They describe the clockwork of the cosmos with stunning precision. Imagine you're watching a video of Earth orbiting the Sun. Now, play that video in reverse. The Earth would just trace its orbit backwards. To an alien physicist who knows nothing about us, the reversed video would look just as real as the forward one. Newton's laws are perfectly happy either way. They are, in a word, time symmetric. Let's bring that down to Earth. If you toss a ball in the air, it makes a perfect arc. Up, then down. If you recorded it and played it backward, the ball would trace that exact same arc, just in reverse. Ignoring air resistance, the reversed video would look totally normal. The underlying physics is completely reversible. And this isn't just some old-school Newtonian quirk. The same holds true for the equations governing electricity and magnetism, and even for Einstein's theory of general relativity, our modern picture of gravity. These pillars of physics describe the asterisk how of the universe's machinery, but they give us no built-in before or after. They contain no arrow of time. So, what gives? We've got a huge contradiction. Our entire lives are a story of irreversible change. We get older, not younger. We remember the past, not the future. We see ice cubes melt in a warm room, but we never see a puddle of water suddenly freeze itself back into a cube. Yet the microscopic laws governing every single water molecule in that cube are perfectly happy to run in reverse. It's like having a car that's perfectly designed to drive forwards and backwards with equal ease, but for some reason, it's stuck on a one-way street, only ever moving forward. If the basic rules of the game don't provide a direction for time, what does? To find the answer, we have to leave the world of individual particles and enter the world of statistics, probability, and chaos. We need to talk about entropy. The hero arrives, introducing entropy. The word entropy can sound a little intimidating, like something out of a dense textbook. But it's a concept so intuitive you already get it. Entropy is basically a measure of disorder, or randomness. And the second law of thermodynamics, one of the most battle-tested laws in science, says that in an isolated system, total disorder, total entropy can only increase. It can never, ever decrease on its own. This is the law that breaks the symmetry. This is the law that gives time its arrow. Forget physics for a second and think about your bedroom. There's really only one way for your room to be perfectly tidy. Every book on the shelf, every shirt in the closet. But how many ways can it be messy? A practically infinite number. Clothes on the floor, on the chair, under the bed. Statistically, a messy state is just overwhelmingly more probable than a tidy one. Left on its own, your room won't spontaneously tidy itself. It will naturally drift towards one of the countless states of disorder. That's entropy. Okay, let's put on the lab coats again. Imagine a box with a divider in the middle. On one side, we put a gas made of 1,000 atoms. This is a pretty ordered, low entropy state. All the atoms are contained in one half. Now, we pull the divider out. The atoms start zipping around randomly. What happens? They spread out, more or less evenly, through the whole box. The system has gone from a low entropy state, ordered, to a high entropy state, disordered. Now, could all those atoms, just by pure random chance, all end up back in the left half of the box? Well, in theory, yes. The laws governing each atom are reversible. But in practice, it's statistically impossible. With just 1,000 atoms, the odds are so tiny you'd have to wait many, many times the age of the universe to see it happen. There's only one way for them all to be on the left, but there are trillions upon trillions of ways for them to be spread out. The system moves toward high entropy simply because there are vastly more ways to be disordered than to be ordered. This isn't some force pushing things toward chaos. It's just simple, brutal probability. This explains why a hot cup of coffee always gets cold. The energy, once concentrated in the coffee, a low entropy state, has way more ways to exist when it's spread out between the coffee and the air. A high entropy state. Heat flows from hot to cold because the uniform temperature state is just statistically more likely. It's why a drop of ink spreads out in water. It's why we remember the past but not the future. Making a memory in your brain is a physical process that, like everything else, increases the total entropy of the universe. Our psychological arrow of time is tied directly to the thermodynamic arrow of time. So, the arrow of time isn't a fundamental property of time itself. It's an emergent property of matter and energy. It is our perception of the universe's relentless, statistically driven journey from order to chaos. But this just pushes the question back. If the universe is always getting more disordered, it must mean that in the past, it was more ordered. A lot more ordered. So, where did all that initial order come from? For that, we have to go back to the beginning. The cosmic blueprint. From the Big Bang to you. The second law of thermodynamics explains why the arrow of time points forward. But for there to be an arrow at all, it needed a starting line. For entropy to be increasing today, it must have started out unbelievably low. If the universe had been born in a state of maximum chaos, nothing would ever change. There'd be no before and after, and no arrow of time. The fact that our universe is filled with incredible structures, stars, galaxies, is the ultimate proof that it began in a state of mind-boggling order. The source of time's arrow is the Big Bang itself. Now, this might sound completely backward. We think of the Big Bang as a fiery, chaotic explosion. And it was incredibly hot and dense. But in the language of thermodynamics and, most importantly, gravity, it was a state of exquisite low entropy. Here's why. In a universe ruled by gravity, a smooth, uniform soup of stuff is actually a very low entropy, highly ordered state. Gravity wants to pull things together. Over cosmic time, it will take a smooth gas and pull it into lumpy stars and galaxies. So, the most probable, high-entropy state for a universe with gravity isn't a uniform soup, but a universe where all matter has collapsed into black holes. The early universe was astonishingly uniform, a hot, dense, mind-bogglingly smooth cosmic plasma. That smoothness was its profound order. It was like starting with a perfectly flat sandbox instead of one where all the sand is already in a few giant clumps. This smooth state had incredibly low gravitational entropy. It held a vast potential for things to happen, for structure to form, and for entropy to grow. And the last 13.8 billion years of cosmic history? That's just been the universe following the second law, unfolding from that special, low entropy starting point. The arrow of time we feel every single second was fired at the moment of creation. Gravity started pulling that smooth gas into the first stars. Stars are magnificent engines of entropy. They take ordered fuel, like hydrogen, and through fusion, spit out disordered heat and light into the void, massively cranking up the universe's total entropy. That disordered sunlight is what powers life on Earth. A plant takes in low-entropy sunlight to build ordered structures, leaves and stems out of disordered molecules like carbon dioxide. But in doing so, it releases waste heat, contributing to an even bigger overall increase in the universe's disorder. When you eat that plant, you're using its stored, low-entropy energy to maintain the fantastic, complex order of your own body. Every single thing you do, every thought, every breath, every memory is a process that maintains a tiny island of order at the cost of increasing the universe's total chaos. Your very existence is only possible because the universe started out so orderly and has been running down ever since, providing the flow of energy that life needs. So, the scrambled egg, your memories, the Milky Way galaxy, they're all just different ripples from the same initial splash. The universe's journey from the special, low-entropy state of the Big Bang. We are temporary, intricate patterns that emerge as the universe unfolds along the arrow of time. But what happens when that journey ends? The end of time? Heat death and maximum entropy. The second law isn't just a story about the past, it's also a prophecy. If the universe's entropy is always increasing, it must be heading toward a final state of maximum possible entropy. This theoretical endpoint is called the heat death of the universe. And don't let the name fool you. It isn't a fiery apocalypse, but the exact opposite, a future of ultimate coldness and uniformity. It's a vision of the universe trillions upon trillions of years from now, when everything has settled into a perfect, boring equilibrium. To get there, all the stars have to burn out. The last red dwarfs will flicker and die in maybe 100 trillion years, leaving behind a graveyard of cold, dead stars and black holes. But even then, entropy's march isn't over. Over timescales that are almost impossible to imagine, even matter itself might dissolve. And the black holes, the universe's ultimate trophies of high-entropy clumping, will slowly evaporate away through a process called Hawking radiation over googles of years. That's a 1 followed by 100 zeros. What's left is heat death. A universe so vast it's nearly empty, filled with just a whisper-thin, near-zero temperature bath of stray particles. A universe where everything is the same temperature. There's no more order left to destroy. The universe has finally reached its most probable state. Perfect, unending disorder. And in that state, something profound happens. The arrow of time dissolves. Remember, time's arrow is just our perception of entropy increasing. But in a universe at maximum entropy, nothing changes. Entropy can't go any higher. The distinction between past and future becomes meaningless. All meaningful processes would stop. There can be no life, no thought, no memory, because all of those things require an increase in entropy. In the desolate stillness of the heat death, time, as we know it, would effectively end. Now, is this fate set in stone? Not necessarily. Physicists are kicking around other wild ideas, a big rip, where dark energy tears space apart, or a big crunch, where the universe collapses back on itself, maybe even resetting the arrow of time. But based on what we know right now, this slow, cold fade to black is the most likely end. So, we come full circle, right back to that scrambled egg. The reason you can't unscramble it isn't some random rule of cooking. It's a direct consequence of the fact that our universe began in a state of extraordinary, special order. The arrow of time isn't baked into the fundamental laws of physics. It's a feature of the universe's unique history. Those laws are the rules of the game, But the game started with a very specific board setup: the low-entropy Big Bang. The entire story of the cosmos is just the universe playing out that game, moving from that one special starting position towards one of the countless disordered end states. The flow of time we feel is our view of this grand cosmic story unfolding. Every shattered glass and every fading memory is a small echo of the universe's journey from order to chaos. We aren't being pushed forward by some river of time. We are living inside the universe's relentless slide into its most probable state. And this journey has a destination. A future of ultimate stillness where the very direction of time ceases to mean anything, bringing the whole story to a quiet, cold, and eternal close. It's a staggering thought that the most personal feeling we have of moments passing is tied to the grandest story of all. The story of the universe itself, from its first fiery, ordered moment to its last, frozen breath. The scrambled egg isn't just breakfast. It's a lesson in cosmology. If you enjoyed unraveling this cosmic mystery, make sure to subscribe and hit that notification bell. And let me know in the comments, what other big scientific questions do you want to explore? The cosmic glitch that splits reality in two. What if, right now, you existed in two realities at once? Not in a sci-fi movie, but at the violent, chaotic edge of our universe. What if there was a place where one event could happen in two totally different ways, at the exact same time? This isn't some philosophical riddle. It's a prediction made by our most fundamental theories of physics. At the boundary of a black hole, the laws of reality as we know them seem to fracture, creating what you could only call a cosmic glitch. From the safety of the outside world, you'd be seen to slow down, stretch, and freeze in time for all eternity, like a statue marking a celestial tomb. But for you, your journey would feel completely normal. You'd feel nothing unusual as you slipped across this invisible line. So, how can you be both an eternal, unmoving monument and a freely falling traveler at the same time? The answer doesn't just tell us about black holes. It reveals a deep and terrifying crack in our understanding of reality itself, forcing us to ask a wild question. Is a single, shared universe nothing more than a stubborn illusion? The lure of the abyss. To understand how reality breaks, we first have to go to the place where it happens. Our journey takes us to one of the most extreme objects in the cosmos, a black hole. From far away, it's an object of impossible simplicity. A perfect sphere of absolute blackness, punched right out of the star-filled fabric of space. It doesn't shine. It doesn't reflect. It only takes. Its silhouette is a stark, silent announcement that something is missing from the universe. This void is what's left of a giant star, many times more massive than our sun, that reached the end of its life. After running out of nuclear fuel, the star lost the fight against its own immense gravity. In one final, catastrophic moment, its core collapsed in on itself, forever. Imagine squeezing Mount Everest into the size of a sugar cube. Now, imagine squeezing a mass many times that of our sun into a space infinitely smaller. The result is an object with nearly infinite density. At this point, gravity stops being just a force that pulls things down. It becomes an absolute, inescapable feature of the space around it. It's a cosmic monster, born from a dead star's collapse, a gravitational singularity so powerful it begins to warp and twist the very fabric of spacetime itself. As our imaginary spacecraft gets closer, we can see the universe start to contort. Starlight from behind the black hole bends around it, creating a warped halo, a phenomenon called gravitational lensing. The blackness itself seems to pull the sky into a swirling vortex. At the center of this distortion is our destination, the source of the paradox to come. The event horizon. The event horizon is probably one of the most misunderstood concepts in all of physics. It's often shown as a physical surface, some kind of shell you could crash into. It's nothing like that. The event horizon isn't a place, it's a point of no return. It's an invisible, geometric boundary in spacetime, defined by one terrifying rule. The speed you'd need to escape its pull is faster than the speed of light. A good, though not perfect, analogy is a massive waterfall. Far from the edge, a boat can easily turn around and sail away. But as it gets closer, the current gets stronger. There's an invisible line in the water where the river is flowing faster than the boat's top speed. Once the boat crosses that line, it doesn't matter how powerful its engine is. It can never fight its way back upstream. The current will inevitably carry it over the edge. The event horizon is like that line in the river, but for spacetime itself. Because nothing can travel faster than light, anything that crosses the event horizon is caught in an unstoppable, one-way current of spacetime. Not even light can escape. It is the ultimate one-way door in the universe. For our thought experiment, let's imagine we're in a command ship, orbiting a supermassive black hole like Sagittarius A*, the 4 million solar mass giant at the center of our own Milky Way. We're at a safe distance, but we're sending in a probe, a brave, uncrewed vessel to take the plunge for us. It's this probe's journey that will expose the glitch in reality. From our viewpoint, we'll see one version of the story. But the data the probe sends back, for as long as it can, will tell a completely different one. The eternal freeze. Our probe starts its final approach, engines off, surrendering to the immense gravitational pull. On our screens, we watch its steady descent toward that perfect circle of black. This is where things first get weird, and it all comes from an idea Albert Einstein gave us over a century ago. Gravity bends time. In his theory of general relativity, Einstein reimagined gravity. It wasn't some mysterious force pulling objects together. Instead, it was a consequence of mass and energy warping the four-dimensional fabric of spacetime. Think of a bowling ball on a stretched rubber sheet. The ball creates a deep dip. A marble rolling nearby gets deflected by this curve, looking like it's being pulled toward the ball. That's gravity. But Einstein's true genius was realizing this warp affects not just the three dimensions of space, but the fourth dimension of time, too. The deeper you are in a gravitational well, the slower time passes for you, relative to someone in a weaker gravitational field. This isn't just a theory, it's a measurable fact of our daily lives. The GPS in your phone has to account for this. The satellites orbiting Earth are in a slightly weaker gravitational field than we are. Because of this, their onboard clocks run just a tiny bit faster than clocks on the ground, about 38 microseconds every day. If engineers didn't constantly correct for this gravitational time dilation, your GPS would be useless in minutes. We've even measured it on Earth. An atomic clock at sea level will tick just a little slower than an identical clock on a mountaintop, where gravity is weaker. On Earth, these differences are tiny, almost unnoticeable. But a black hole is not the Earth. It's gravity taken to its absolute, most violent extreme. As we watch our probe fall, this effect goes into overdrive. The probe has a clock on board, flashing once per second. From our perspective on the command ship, something bizarre starts to happen. The flashes slow down. The 1 second interval becomes 2 seconds. Then 10. Then a minute. The closer the probe gets to the event horizon, the deeper it sinks into that gravitational well, and the more drastically time on the probe slows down for us. It's not just the clock, either. Everything about the probe appears to slow. If it were firing its thrusters, the bursts would seem to last longer and longer. If an astronaut inside were waving at us, their arm would move with agonizing slowness, as if trapped in cosmic amber. At the same time, a second effect takes over. The light from the probe is fighting its way out of an impossibly deep gravity well to reach us. This struggle robs the light of its energy. In the light spectrum, blue light is higher energy and red light is lower energy. As the probe's light loses energy, it gets shifted toward the red end of the spectrum. This is known as gravitational redshift. First, the probe's bright white beacon turns a pale yellow, then a deep orange, then blood red. As it gets even closer to the horizon, the light continues to redshift, past what we can see, into infrared, then microwaves, then long, lazy radio waves. Eventually, the signal becomes so stretched out and weak that our instruments can't detect it at all. The probe fades away. When you combine these two effects, infinite time dilation and infinite redshift, you get the first reality. From our point of view, the probe never, ever crosses the event horizon. We watch it get slower and redder, approaching that invisible line at an infinitely slowing pace. The instant before it crosses is stretched out before us for an infinite amount of our time. To us, the probe is frozen, a ghostly image plastered onto the edge of the black hole for all eternity. We could watch for billions of years, and from our perspective, that probe would not have moved an inch. This isn't an optical illusion. According to the laws of physics governing our command ship, this is what is genuinely happening. Our clocks tick normally, our reality moves on, and in that reality, the probe is forever trapped on the boundary. This is reality number 1. The swift passage. So, let's switch perspectives. Let's forget the command ship and see the universe from the probe's point of view. What does our brave little robot actually experience? Here's the key to the whole paradox. Absolutely nothing special. Inside the probe, its internal clock keeps ticking away, 1 second per second, perfectly normal. This is what physicists call proper time, the time you experience yourself. It feels completely normal. If an astronaut were inside, their heart would beat normally. They could make coffee, read a book, run a systems check. They'd have no feeling of time slowing down. From their perspective, it's the asterisk outside universe that's going haywire. Looking back at our command ship, they'd see events there speeding up wildly. A 1-hour message we send might be received in just a few seconds. They'd see the stars of the galaxy wheel and turn at a fantastic rate, watching cosmic history play out on fast forward. But the main event crossing the event horizon is, from the probe's point of view, shockingly boring. There's no wall, no fiery gate, no jolt. The probe simply sails across the invisible line. One moment it's outside, the next, it's inside. Without incredibly precise instruments, the probe would have no idea it just passed the point of no return. Once inside, however, the rules of the game change completely. Before, the probe could theoretically fire its engines and escape. Now, it's locked into its fate. That's because inside the event horizon, space and time themselves get twisted and swapped. Think about your life. You can move freely in the 3 dimensions of space: left, right, up, down. But you have zero freedom in time. You are dragged forward, into the future, second by second. You can't stop, and you can't go back. Inside a black hole's event horizon, the direction toward the center, the singularity, becomes like time. The singularity is no longer a place in space, it's a moment in your future. And just like you can't avoid next Tuesday, the probe cannot avoid the singularity. All possible paths lead to it. Firing the engines in any direction only makes you get there faster. What that final journey is like depends on the black hole's size. For a small, stellar mass black hole, the end would be violent and quick. The pull on the front of the probe would be so much stronger than on the back that these tidal forces would stretch it apart, atom by atom, in a process graphically known as spaghettification. But we're falling into a supermassive black hole. Here, the story is different. The event horizon is so huge that it's much farther from the center. The spacetime curvature at the horizon is actually quite gentle. The difference in gravity between the probe's front and back would be tiny. An astronaut could cross the event horizon of a supermassive black hole without feeling a thing, surviving for hours or even days in their normal time before the tidal forces closer to the center became lethal. So, this is reality number 2. A completely valid story described by the same laws of physics. In this reality, the probe's time flows normally, it crosses the horizon without any drama, and it continues its journey, doomed, yes, but experiencing a finite, uninterrupted trip all the way down. We're left with an impossible situation. Two contradictory realities, both predicted by the same science. In one, our probe is an eternal, frozen relic. In the other, it slips past the edge in the blink of an eye. How can both be true? Before we try to stitch reality back together, if you enjoy having your mind bent by journeys to the edge of physics, consider subscribing. We explore the cosmos every week, and you help make it possible. The Cosmic Glitch. This is the Cosmic Glitch. An event that both happens in a finite, uneventful moment, and also never happens at all. An object is simultaneously in two places, in two states of being. It's both moving normally and frozen for eternity. This isn't just a fun puzzle. It seems to violate a core principle of the universe. That an event either happens or it doesn't. So, who's right? The command ship watching from afar, or the probe taking the plunge? According to Einstein's relativity, they both are. The permission slip for this contradiction comes from the very heart of his theory. There is no single, universal, now. Time is relative. What is now for you depends entirely on your motion and your position in a gravitational field. The key to why physics allows this split in reality is the absolute, unbreakable communication barrier created by the event horizon. The command ship sees the probe freeze because the last bit of information from the probe just before it crosses the horizon takes an infinite amount of time to climb out of that gravity well and reach us. Meanwhile, once the probe crosses the horizon, it can never send a signal back out to say, "Hey, I made it. I'm inside." Any signal it sends is caught in the inward flow of spacetime and dragged to the singularity. It can no more send a message to the outside universe than you can mail a letter to the 18th century. Because the two observers can never compare notes, physics doesn't have to reconcile their two stories. They are two separate, causally disconnected realities. There's no logical paradox, because a paradox would require one person to see two contradictory things at once. Here, the two contradictory stories are held by two observers who can never, ever talk to each other again. The glitch is a direct result of time not being a universal clock. It's a local, flexible thing. The now of the command ship and the now of the falling probe are two fundamentally different slices of spacetime. And at the edge of a black hole, these slices become so misaligned that they tell two completely different stories about the same object. The why, unraveling the universe. So, this glitch isn't a mistake in the math. It's a feature that general relativity predicts. But what does it mean? It matters because this very paradox has been a guiding light for physicists for 50 years, pointing the way toward an even deeper layer of reality. It forces us to confront an even bigger mystery, the black hole information paradox. The problem starts when you bring in the other great pillar of modern physics, quantum mechanics. One of the unbreakable laws of the quantum world is that information can never truly be destroyed. You can burn a book, but if you could collect every particle of smoke and ash and measure their exact states, you could, in principle, reconstruct the book. The information gets scrambled, but it never vanishes. So here's the paradox. What happens to the asterisk information in our probe when it falls into a black hole? Relativity says it falls in, gets crushed at the singularity, and is lost from our universe forever. Quantum mechanics says that's impossible. The information must be preserved. In the 1970s, Stephen Hawking made the problem even worse. He showed that black holes aren't perfectly black. They should slowly emit a faint thermal glow, now called Hawking radiation. Over unimaginable timescales, this radiation causes the black hole to lose mass and, eventually, evaporate into nothing. So, Where did the information go? If the black hole is gone, and the information isn't inside it, and the radiation it spat out was random, then the information was truly destroyed. The universe deleted something. This violates the sacred laws of quantum physics. And this is where our cosmic glitch comes back to save the day. What if both realities, the frozen one and the falling one, are somehow true at once? This led physicists like Gerard T. Hooft and Leonard Susskind to a radical, mind-bending proposal: the holographic principle. The holographic principle suggests that the 3D reality we experience might be an illusion, a projection of information that's stored on a distant, 2D surface. Think of the hologram on a credit card. It's a 2D surface that holds all the information to create a 3D image. The idea is that maybe our entire 3D universe is written on some distant 2D boundary. How does this help with black holes? The paradox of the frozen observer gives us a clue. From our outside perspective, everything that ever fell into the black hole seems to be frozen and smeared across the 2D surface of the event horizon. The holographic principle takes this literally. It suggests the information of our 3D probe isn't lost inside the black hole. It's asterisk encoded on the surface of the event horizon itself. In this view, the glitch isn't a glitch. It's two different ways of describing the same thing. The outside observer's story, where the probe is a frozen layer of information on the 2D horizon, is the holographic description. The probe's own story, where it exists in 3D space and falls through, is the projected image. This incredible idea suggests that, from our point of view, information never truly crosses the horizon. It gets encoded there. And when the black hole evaporates, the Hawking radiation comes from that horizon, and it can carry the information back out into the universe in a very scrambled form. Information isn't destroyed. Quantum mechanics is saved. And the price is the idea that our three-dimensional reality might just be a complex projection. We started with a journey to a black hole, hoping to understand a weird feature of spacetime. We're ending with the unsettling possibility that spacetime itself isn't even fundamental. The cosmic glitch, the idea that one object can be both frozen for eternity and falling freely, isn't a mistake in the universe's code. It's the universe showing us the source code. It's a clue that what we see as a solid, 3D reality could be a grand illusion, a hologram projected from a 2D canvas at the edge of space and time. Black holes are the ultimate cosmic labs. They're where our best theories, general relativity and quantum mechanics, get pushed to their breaking points. And in those breaking points, we don't find errors, we find revelations. The contradictions they create force us to let go of our most basic ideas about what reality even is. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And what we see as a glitch might just be the whisper of a deeper, more elegant, and far more bizarre truth about the nature of everything. Your brain is lying to you about time. You feel it right now. A silent, invisible river carrying you from one moment to the next. The steady, relentless march of seconds turning into minutes, minutes into hours. You call it time. It governs your life, structures your memories, and defines your sense of reality. You're born, you live, and you die, all on its unyielding current. It feels fundamental, absolute, real. But what if I told you that this feeling is a lie? A grand illusion crafted by your own mind for your own survival. What if the most fundamental, bedrock rules of the universe, the equations that describe reality at its deepest level, have no mention of time at all? The science is pointing to a shocking conclusion. Time, as you experience it, doesn't exist. It's not a law of the universe. It's a story your brain tells itself. So, what is really going on? What is this phantom that rules our lives? And if time isn't real, then what are you? The clockwork god and the absolute river. To understand where physics says time breaks down, we first have to get our heads around the idea of time we all carry with us. It's an idea that feels so natural, so intuitive, that for most of human history, we never even thought to question it. This is the world of classical physics, the world of Sir Isaac Newton. In the 17th century, Newton gave us the picture of a clockwork universe. Imagine a colossal, intricate machine, set in motion by a divine watchmaker, operating according to precise, unbreakable laws. In this universe, everything had its place, and every event could be predicted if you just knew the starting conditions. And flowing through this whole cosmic machine was a single, universal river: absolute time. Newton described it as something that, of itself, and from its own nature, flows equably without relation to anything external. What he meant was that time was the ultimate metronome of reality. A second passing for you on Earth was the exact same second passing for a hypothetical alien on the most distant star in the cosmos. It was independent, constant, and the same for everyone, everywhere. It was the master clock of the universe. This idea is baked deep into our psychology. We imagine a universal now that we all share. When you look up at the moon, you feel as though you are seeing the moon right now. When you talk to someone on the other side of the world, you believe you're both existing in the same slice of the present moment. This Newtonian view is comfortable. It gives us a shared stage on which the drama of the universe unfolds. Space is the arena, and time is the unstoppable clock that ticks forward for every actor, from the smallest dust mote to the largest galaxy. For over 200 years, this was the unshakable foundation of physics. It worked perfectly. Newton's laws could predict the orbits of planets, the arc of a cannonball, and the swing of a pendulum. Everything was predictable, everything was orderly, and time was the reliable, absolute backdrop against which it all happened. It was a beautiful, elegant, and reassuring picture of reality. There was just one problem. It was completely wrong. The first crack in this perfect clockwork facade came not from a philosopher, but from a humble patent clerk in Bern, Switzerland. His name was Albert Einstein, and he was about to prove that the universal river of time was just a mirage. The master clock of the universe, it turned out, was broken. Or rather, it had never existed in the first place. The disruption: Einstein's spacetime revolution. The year is 1905. While the world is preoccupied with industry and politics, Albert Einstein publishes a paper called On the Electrodynamics of Moving Bodies. It introduces his theory of special relativity, and with it, the entire Newtonian clockwork universe starts to unravel. Einstein's revolution began with a simple, yet profoundly weird, observation about light. Experiments had shown something impossible. The speed of light in a vacuum is constant. It doesn't matter if you are standing still, or if you're racing towards the light source, or flying away from it. No matter your own motion, you will always measure the speed of light to be exactly the same. About 299,792 kilometers per second. This might not sound world-shattering at first, but think about it. Imagine you're on a train moving at 100 kilometers per hour, and you throw a ball forward at 20 kilometers per hour. For someone on the platform, the ball is moving at 120 kilometers per hour. Speeds add up. That's common sense. But light refuses to play by these rules. If you're on that same train and turn on a flashlight, both you and the person on the platform will measure the light from that flashlight moving at the exact same speed. Einstein took this bizarre fact and followed it to its logical conclusion. He realized that if the speed of light is constant for everyone, then something else must be changing to compensate. That something else was space and time. He showed that time is not an absolute, universal river. Instead, it is relative. It depends on your motion. This is the famous concept of asterisk time dilation. The faster you move through space, the slower you move through time relative to someone standing still. This isn't a trick of perception, it's a physical reality. If you were to board a spaceship and travel near the speed of light for what feels like a year to you, you'd return to Earth to find that decades, or even centuries, had passed. Your clock, your heartbeat, your aging process all would have genuinely slowed down compared to those you left behind. This isn't science fiction. We see it in action every single day with the GPS satellites orbiting our planet. They are moving at thousands of kilometers per hour, which causes their clocks to run slower than clocks on Earth by about 7 microseconds each day due to special relativity. But that's not all. A decade after his first theory, Einstein expanded on these ideas with his theory of general relativity. He realized it wasn't just speed that could warp time, gravity could, too. He proposed that gravity is not a force, but a curvature in the very fabric of reality. A single, four-dimensional continuum called asterisk spacetime. Massive objects like planets don't just sit in space. They warp spacetime around them like a bowling ball on a trampoline. What we feel as gravity is just us following the curves. This warping also affects time. The stronger the gravity, the slower time passes. Because the GPS satellites are in a weaker gravitational field than we are on the surface, their clocks actually tick faster by about 45 microseconds per day. Combine the two effects, and the clocks on GPS satellites get ahead of clocks on Earth by about 38 microseconds every day. It's a tiny amount, but if engineers didn't constantly correct for it, the entire GPS system would fail within minutes, racking up positioning errors of about 10 kilometers per day. Your phone's map works because Einstein was right. With relativity, there is no universal now. The idea that we all share a single present moment is an illusion. Your now is different from the now of someone moving relative to you. This led physicists to a startling new model of the universe called the asterisk block universe. If past, present, and future are all relative, then one logical way to picture reality is as a single, static, four-dimensional block of spacetime containing all events that have ever happened and ever will happen. Your birth, you reading this sentence, and every moment of your life are all just different coordinates in this static block. The flow of time, in this view, is a purely subjective illusion. Einstein himself was a firm believer in this. When his lifelong friend Michel Besso died, he wrote to the family, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion." For Einstein, all of spacetime existed at once. But even this radical idea doesn't get to the heart of the problem. Because as physics pushed deeper, into the realm of the impossibly small, it found that time doesn't just get bent. It seems to disappear entirely. The deep dive into the quantum froth. Einstein's theories revolutionized our view of the grand scale of the universe. But at the same time, another revolution was exploring the universe on the smallest possible scale, quantum mechanics. And it's here that the concept of time truly begins to dissolve. Imagine zooming into the fabric of reality, far past what any microscope can see. Past molecules, atoms, and even the protons and neutrons inside. You keep zooming until you reach a scale so small it defies imagination. The asterisk Planck length. If you scaled up a single atom to the size of the known universe, the Planck length would be about the height of a tree. This isn't just a tiny distance. It's what many physicists believe is the fundamental pixel of reality. At this scale, our smooth picture of spacetime completely breaks down. Welcome to the asterisk quantum foam. This idea, first proposed by physicist John Wheeler, suggests that at the Planck scale, spacetime isn't smooth at all. Instead, it's a chaotic, roiling, frothy mess. Thanks to quantum uncertainty, the fabric of spacetime itself is subject to violent fluctuations. Virtual particles are constantly bubbling into existence and vanishing. Microscopic wormholes might be popping in and out of the vacuum like bubbles in a boiling pot. In this realm, the classical notions of here and there, before and after, lose all meaning. The smooth, orderly progression of time we experience might just be a large-scale average of this underlying quantum chaos, much like the sensation of temperature is an average of the chaotic motion of countless individual molecules. This means time isn't fundamental. It must be an emergent phenomenon something that arises from a deeper, timeless reality. This isn't just philosophy. It's a huge problem at the heart of modern physics, known as the problem of time. Our two great theories, general relativity and quantum mechanics, describe time in completely incompatible ways. To create a unified theory of everything, physicists have to figure out how to make them play nicely. The most famous attempt to do this led to an equation that only deepened the mystery: the Wheeler-DeWitt equation. Formulated by John Wheeler and Bryce DeWitt, it was an attempt to write down a quantum description of the entire universe. But when they wrote it, they discovered something shocking. The variable for time, t, was completely absent. It had vanished from the equation. According to one interpretation of the Wheeler-DeWitt equation, at the most fundamental level of reality, there is no change, no flow, no time. Now, it's important to say this is still heavily debated. Many physicists think the equation's timelessness is a clue that we're misunderstanding something profound. Perhaps time isn't a background feature of the universe, but something that emerges from the relationships between things. In this view, there is no master clock, there are only clocks. And a clock is simply any physical system that changes in a predictable way that we can compare to other changing systems. The flow of time we perceive is just our brain tracking the changes in one thing, like our own thoughts, relative to another, like the sun's position in the sky. This leads to a huge question. If spacetime is fundamentally a pixelated, jittery foam, shouldn't we be able to see it shaking? The hunt for quantum jitters. The idea that spacetime might be a seething foam isn't just a wild theory. It makes a testable prediction. If space and time aren't smooth, then everything should have a tiny, unavoidable jitter, as it's carried along by these quantum fluctuations. For decades, this was thought to be too small to ever measure. But recently, incredibly sensitive experiments have started hunting for this cosmic tremor. One of the first major attempts was the holometer experiment at Fermilab. This device was a laser interferometer designed to look for a specific kind of spacetime jitter. It used two powerful lasers, split them, sent them down 40-meter arms, and then recombined them. If spacetime were perfectly still, the beams would recombine perfectly. But if spacetime itself were jittering, it would subtly change the length of the arms, causing the laser light to flicker. After a year of taking data, the holometer team announced its results around 2015. They found nothing. The experiment ruled out the specific model of jitter it was designed to test, which was still a crucial piece of science. It set important limits, showing that if this quantum jitter exists, it's either smaller than that model predicted, or it behaves differently. But the hunt is far from over. The most sensitive instruments ever built are the massive interferometers of the LIGO Virgo KAGRA, LVK collaboration, the observatories that first detected gravitational waves. These detectors, with arms stretching for kilometers, are also perfect tools to search for the subtle, high-frequency hum of quantum foam. The fourth observing run, known as O4, was a massive success, beginning in May 2023 and officially concluding on November 18, 2025. It generated a treasure trove of new gravitational wave candidates, more than doubling the total number of detections from all previous runs combined, and scientists are now poring over the data. While their main goal is astrophysics, they're also looking for any strange noise that can't be explained by normal sources. This data offers an unprecedented chance to search for the signature of spacetime fluctuations, though no definitive detection has been announced yet. After a period of upgrades, the next run is planned to begin in late 2026. The challenge is knowing exactly what to look for, as different theories of quantum gravity predict different kinds of jitter. Theorists are constantly developing new frameworks and models to guide this search, essentially creating a roadmap for experimentalists. Instead of searching blindly, they can now look for specific signatures in their data. The hunt for quantum jitters is science at its most fundamental. We are building machines at the absolute limit of our technology to look for a tremor in the very bedrock of reality. If a signal is found, it will be the first experimental evidence that time is not fundamental, but emerges from a deeper and far stranger quantum world. The master illusionist, your brain. So, physics seems to be screaming at us that our everyday experience of a forward-flowing river of time is a profound illusion. But if that's true, why does it feel so overwhelmingly real? If the universe is a static block or a timeless quantum state, who is creating the movie we call our lives? The answer, it seems, lies within the 3 pounds of wrinkled tissue between your ears. The master illusionist is your own brain. Our brains didn't evolve to understand quantum gravity. They evolved for survival. On the savannah, being able to distinguish between before and after was life or death. You need to remember where the predator was to predict where it will be. To make sense of the flood of sensory information, the brain constructs a narrative. It takes the static frames of reality and strings them together into a coherent story. The perception of time's flow is the user interface it built for reality. It's just not reality itself. Recent neuroscience is starting to show how this illusion is built. The prevailing view is that our brains don't seem to have a single, central clock. Instead, our perception of time passing is closely tied to the number of events or experiences we process. As researchers from the University of Sussex and UNLV have explored, when we're busy and engaged, our brain is processing a lot of stuff, and time seems to fly. When we're bored and nothing is happening, our brain has few new events to process, and time seems to slow to a crawl. This is why time flies when you're having fun is a deep insight into our neural architecture. Studies suggest our brain activity is more of a counter than a clock, tallying experiences to create a sense of duration. This helps explain why our sense of time is so subjective. A traumatic event can seem to unfold in slow motion, likely because the brain is in hyperarousal, processing an enormous amount of information and stretching out that moment. Conversely, as we get older, time often seems to speed up. A possible reason is that as we age, we have fewer novel experiences. A childhood summer felt like an eternity because every day was filled with new discoveries. A year in our adult life, filled with routine, can feel like it passes in a blink because it contains fewer memorable events for the brain to count. The brain's job is to create a simplified, useful model of the world. It takes the chaotic, timeless reality suggested by physics and projects it onto a simple, linear timeline. This timeline allows us to form memories of the past and make plans for the future. It gives us our sense of identity, a continuous self that persists through time. The perception of now is perhaps the most powerful part of this illusion. It feels like a spotlight moving along the timeline. But physics provides no basis for a special, universal present moment. Your now is a construction of your consciousness, a brief window where memory transitions into anticipation. As neuroscientist and philosopher Sam Harris puts it, the past is a memory, the future is an anticipation, and the present is a fiction. So, the feeling that you are a self being carried forward by the river of time is a story woven by your own mind. It's an essential story for our sanity and survival. But it is a story. The ultimate truth may be that we are not travelers on the river of time. We are the river patterns embedded in spacetime. The brain is just a mechanism within that pattern that has evolved to perceive it, one moment at a time. If these ideas are stretching your mind, and you want to keep questioning the fundamental nature of reality, then make sure to subscribe and hit that notification bell. We dive into mind-bending topics like this every week, and you won't want to miss what's next. And if you know someone whose perception of time needs a little shake-up, share this video with them. Living in a timeless world. We've journeyed to the very edge of physics and back. We've seen time bend and stretch, we've peered into the quantum foam where it seems to vanish, and we've uncovered our own brain's role in creating this grand illusion. So, where does that leave us? The implications are profound. If the universe is a static block, where the future is as fixed as the past, what does that mean for free will? Is our sense of making choices just an illusion as we experience a pre-written path? Some physicists and philosophers would argue yes. Our lives may be like a movie, the story is already complete, but the character inside doesn't know what's coming next. On the other hand, the randomness of quantum mechanics might offer an escape clause. The honest answer is, we don't know. But there's also a more personal takeaway. Understanding that the relentless pressure of time's passage is a product of our own minds can be incredibly liberating. The anxiety we feel about the future and the regret we hold about the past are tied to this illusion of a fleeting timeline. Realizing that, now, is the only reality we ever truly have access to can be a powerful tool for mindfulness. It encourages us to engage more fully with the present moment, knowing it isn't just a fleeting point between a fixed past and an uncertain future, but a vibrant and complete experience in itself. The science of time is a humbling journey. It shows us that our most basic intuitions about the world can be profoundly wrong and reveals a universe far stranger and more mysterious than we could have ever imagined. The problem of time remains one of the biggest unsolved mysteries in science. But the quest continues. The truth might be that there is no fundamental clock, no universal now, and no unstoppable river. There is only the intricate, timeless, quantum dance that somehow, miraculously, gives rise to the universe, to us, and to the beautiful, persistent, and utterly convincing illusion of a moment passing by. Quantum physics just disproved cause and effect. There's a place where the past, present, and future are one. Where a single particle can seemingly make a choice with no clock to guide it, and where the most basic rule of our reality that A has to happen before B can happen just shatters. This isn't science fiction. This is the weird, established, and experimentally proven world of quantum physics. Now, about the title of this video. Quantum physics just disproved cause and effect. Let's get this out of the way. That statement is wrong. But it's wrong in the most interesting way imaginable. Because what quantum mechanics has actually done is way stranger than just killing causality. It's forced us to wonder if causality ever needed time in the first place. It suggests that the whole story of our lives, of history, of the universe itself, might not be a river flowing from past to future, but a single, frozen sculpture. And our feeling of before and after, just a stubborn illusion. Today, we're going to peel back the layers of reality. We'll start with the mind-bending antics of single particles, then look at the logic that could run a timeless universe, and finally, we'll go all the way back to the Big Bang, the ultimate edge where time itself breaks down. What you're about to hear will challenge not just what you know about physics, but what it even means to exist. Stay with me, because your understanding of reality is about to get a serious update. The quantum realm's assault on time. Our everyday world runs on a simple, unbreakable rule. Cause comes before effect. You strike a match, then it lights up. A star collapses, then a black hole forms. This straight line of events, this arrow of time, is pretty much the foundation of our sanity. But when you zoom way down to the quantum level, that foundation starts to crack. And it doesn't just crack, it dissolves into a fog of pure possibility. Let's start with the greatest hits, the double-slit experiment. You fire one particle, say, a photon, at a wall with two slits. Common sense says it has to go through one or the other. But that's not what happens. The particle acts like it went through both slits at the same time. It interferes with itself, creating a wave pattern on the screen behind the wall. Think about what that means for time. For the particle to make that pattern, it has to somehow know about both paths at once. It's not like it zips down one path and then dashes back to check out the other. No. In the quantum world, before we look at it, the particle's story isn't unfolding in time. It's a cloud of all possible histories existing together, a superposition. There's no before, it shows a path, or after. It's exploring all its options at once in a way that can only be described as timeless. This timeless state holds up right until the moment we measure it. The instant we try to see which slit the photon went through, the wave pattern disappears. The cloud of possibilities collapses into one single reality. The photon picks a spot, becomes a particle, and lands in a definite now. This is what physicists call wave function collapse. It's the bridge between the bizarre, timeless quantum world and our familiar world of clocks and consequences. Before we measure, the particle is in a timeless haze. After we measure, it snaps into a concrete now, becoming a cause that can lead to a future effect. The quantum heart of reality beats without a rhythm, but the moment it touches our world, it starts the clock ticking for everything else. But if that doesn't feel strange enough, let's talk about quantum tunneling. Imagine throwing a tennis ball at a solid wall. If the ball doesn't have enough energy, it's going to bounce off. Every single time. But in the quantum realm, a particle can do the impossible. It can just appear on the other side of a barrier it shouldn't be able to cross. It's as if it tunneled right through reality. For decades, this led physicists to a terrifying question. How long does the tunneling take? The answers that have come back are unsettling. Some early experiments suggested the particle shows up on the other side so fast, it seems to have traveled faster than a particle that had a clear path. This sparked the explosive idea that tunneling might be instantaneous, or maybe even a faster-than-light phenomenon. Now, let's be crystal clear. The idea of anything traveling faster than light is a massive problem for Einstein's theory of relativity and the whole principle of causality. If you can send something faster than light, you can theoretically send information into the past, creating paradoxes that would completely unravel reality. So, to say this idea is controversial is putting it mildly. The debate has been raging for years, centered on incredible devices like the atto clock. An atto clock uses a laser's electric field, which oscillates incredibly fast, to try and time an electron tunneling out of an atom. For context, an attosecond is to 1 second what 1 second is to the entire age of the universe. Some of these experiments, especially with simple atoms, found that the time it took for the electron to appear was so small it was basically zero. It looked instantaneous. This, however, is where things get tricky. These results are fiercely debated. Other physicists argue that the whole idea of timing the event is flawed. How can you time a particle's journey when it doesn't have a definite position to begin with? They argue that just because the peak of the particle's wave function appears on the other side doesn't mean the whole particle teleported faster than light. More recent theories, like one from physicists Patrick Schock and Enno Gysi, suggest using an atom's internal wobbles as a tiny, built-in stopwatch. Their math suggests tunneling is not instantaneous. It takes a tiny, finite amount of time, something like 10 to the power of minus 26 seconds, and, critically, does not beat the speed of light. So, what's the takeaway here? Even if tunneling isn't truly faster than light and the consensus is that it can't be used to send a message back in time, the whole thing is still a huge break from our classical world. The particle doesn't drill a hole. It doesn't spend time traveling through the wall. Its wave function, the map of where it could be, exists on both sides of the barrier. The chance of it being on one side just vanishes, while the chance of it being on the other side appears. It's a jump, not a journey. In this case, causality doesn't need a timeline. The cause is the quantum state and its probabilities. The effect is the particle appearing on the other side. The link between them isn't a sequence of events, but a probabilistic leap dictated by the timeless laws of quantum mechanics. What all this superposition, collapse, and tunneling shows us is that at rock bottom, reality isn't a sequence of events. It's a static ocean of possibilities. The flow of time and the neat chain of cause and effect we rely on are things that only emerge when we zoom out, when the quantum fog blurs into the classical world. Down in the fog, causality isn't about what happens next, it's about what is possible. And realizing that is the first step toward dismantling our whole idea of time. The logic of timeless causality. We've seen how the quantum world seems to work in a timeless haze, but this opens up a scary question. If time isn't fundamental, if before and after can get fuzzy, does causality just fall apart? If A doesn't have to happen before B, can we still say that A asterisk causes B? The answer, coming from a growing corner of physics and philosophy, is a loud yes. We just have to stop thinking about causality in terms of time and start thinking about it in terms of logic and structure. Let me try an analogy. Think of a math proof. The premises are at the beginning, and the conclusion is at the end. You could say the premises cause the conclusion. But do they happen before the conclusion in time? No. The whole proof exists as a single, static thing. The conclusion is true because the premises are true. The connection is one of logical dependence, not a sequence in time. Here's another one. A house of cards. The bottom card is the cause of the whole thing being stable. If you pull it out, the effect is a collapse. But does the bottom card exist in time before the top card? Nope, the whole thing exists at once. The causality here is structural. The top card's position depends on the bottom card's position. This is what philosophers call a temporal causality. It's the idea that the heart of causation isn't about one thing happening after another, but about one thing fundamentally depending on another. Now, these are just analogies. A math proof or a house of cards aren't the universe. But they show that you can have all the pieces of causation explanation, prediction, dependence without needing a ticking clock. And this isn't just philosophers staring out a window. This way of thinking is showing up in advanced physics. Picture reality as a giant network. A causal link between two events, A and B, just means that the information that defines B depends on the information that defines A. This is exactly how things like Bayesian networks work, figuring out causal links from statistics without needing any time data at all. The arrows of cause and effect are revealed by patterns of dependence, not by a stopwatch. In this view, the arrow of time we all feel doesn't come from some cosmic flow. It emerges from these one-way causal relationships. If B depends on A, but A doesn't depend on B, you've got a direction. You've got an explanation. String enough of those together, and you get a story. You get history. You get what feels like the forward march of time. This switch from a time-based sequence to a structural dependence is radical, but it solves a huge headache. In our best theories of physics, general relativity and quantum mechanics, time is a slippery, ambiguous thing. In Einstein's relativity, you get the block universe, where past, present, and future all exist together in a 4D block of spacetime. In some attempts to create a theory of quantum gravity, time vanishes from the main equations entirely. If physics itself is pointing to a world where time isn't fundamental, then our idea of causality has to be more than just A happens, then B happens. Structural causality is the escape hatch. It lets cause and effect stay as a pillar of reality, even if the flow of time is just in our heads. This brings us to the ultimate boundary, the Big Bang. The moment before which there was no before. If cause and effect absolutely require time, then asking, what caused the Big Bang, is a meaningless question. But if causality is structural, the question is not only meaningful, it might even be answerable. We're no longer asking what happened before the start of time. We're asking, on what timeless, logical foundation does our entire universe depend? This shift in thinking is huge. It suggests the universe isn't a movie being played for us. It's a sculpture. A finished object. Our consciousness is just moving through this sculpture and experiencing it as a sequence. But the sculpture itself, all of it is already there. The cause of the top of the sculpture is the base, not because the base was built first, but because the base holds it up in the final design. The laws of physics, in this picture, aren't rules for how the movie plays out. They're the principles of the sculpture's construction. A universe without a clock. If the quantum world hints at a reality without time, and logic gives us a way for causality to survive there, where does this idea show up in its biggest, most mind-blowing form? The answer is cosmology. And here, we run into one of the most audacious ideas in physics. That the universe as a whole is static, and time is an emergent illusion. The main proponent of this view is the British physicist Julian Barbour. For decades, he's argued that our belief in a flowing river of time is the biggest thing getting in the way of uniting quantum mechanics and general relativity. His idea, often called timeless physics, is definitely a minority view. It's not mainstream, but it's a powerful alternative. Big names in physics like Lee Smolin and Sean Carroll have criticized it, arguing that time is real and fundamental. Barbour asks us to imagine a vast, abstract space containing every possible arrangement of the universe. He calls it Platonia. A single point in Platonia isn't a location, it's an entire universe frozen in one instant. A single now. One point might be a universe that looks like the hot soup of the Big Bang. Another is the universe with you, right now, watching this. Another is a universe where Earth never even formed. Every possible snapshot of any universe exists as a static point in this infinite landscape. So where's time? According to Barbour, it's not there. There's no master clock pushing the universe from one now to the next. All the nows exist at once, timelessly. What we feel as the flow of time, he says, is an illusion created by the relationships between these nows. Your brain, which exists in one particular now, contains memories. But these memories aren't ghosts of a dead past. They are physical structures in your brain in the present now. He calls them time capsules, fixed patterns that create the appearance of a history. Your memory of what you had for breakfast this morning is just a specific pattern of neurons firing right now. That pattern is linked to another, slightly different, now, in Platonia, the one we'd label breakfast time. The arrow of time, that feeling of forward motion, comes from complexity. In his book, The Janus Point, Barbour suggests that the laws of physics naturally favor a structure where complexity grows out from a single, simple point. That central point is what we call the Big Bang. It's not an explosion in time. It's the simplest possible arrangement of the universe, the most boring, now, in all of Platonia. From that point, paths of growing complexity spread out in all directions. Our universe is on one of those paths. We see complexity increasing, stars forming, galaxies clustering, life evolving, and we read that as the forward flow of time. According to Barbour, there could be a whole other universe on the other side of the Big Bang, experiencing time flowing in the opposite direction, with its own arrow of growing complexity. It's a wild idea, but it has a fascinating partner in the quantum world. The Page-Wouters mechanism. Proposed back in 1983, It's a model that shows how the feeling of time can emerge from a completely static, timeless quantum state. Imagine the whole universe as one giant, stationary quantum wave function. It doesn't change. So how do we see anything change at all? The Page-Wooter's idea suggests we can split the universe into parts. Let's say one part is a clock, and the other is the rest of the universe. In this model, the clock and the rest of the universe are quantum entangled. The whole system is static, but the state of the rest of the universe is linked to the state of the clock. So if you're an observer inside this universe, you don't see the static whole. You see the rest of the universe relative to the clock. When the clock is in a state we'd call 1 o'clock, the universe is in a certain state. When the clock is in a state we'd call 2 o'clock, the universe is in a different state. Time, in this picture, isn't fundamental. It's a relationship born from quantum entanglement. The system evolves relative to the clock, not relative to some absolute, cosmic time. It neatly shows how a dynamic, changing world can pop out of a timeless, universal quantum state. It's really important to say that both Barber's Platonia and the Page-Wooter's mechanism are interpretations and theoretical models. They aren't proven facts. Barber's ideas are as much philosophy as physics and aren't really testable, which he's acknowledged. The Page-Wooter's mechanism is a formal model, and scientists are still working on it. But what they both do is give us a glimpse of how a timeless reality could work. They show us a universe where causality is saved, not as a sequence, but as a web of correlations and dependencies. The Big Bang isn't the start of the movie. It's the anchor point of the sculpture. Cause and effect can still work, pushing the universe toward more complex states and creating the illusion of past and future, all without a single tick of a master clock. The universe doesn't need time to exist, it just needs relationships. The superposition of cause and effect. We've gone from the timeless dance of a single particle to the static grandeur of the cosmos. But now we arrive at the most bewildering frontier of all. A place where quantum mechanics doesn't just ask if time is necessary for causality, but seems to shatter the very order of cause and effect itself. What if A could cause B, and at the exact same time, B could cause A? This isn't a riddle. This is the world of indefinite causal order, a concept that has now been demonstrated in real experiments. It is probably the most direct attack on our everyday understanding of cause and effect. In our world, things are locked in a sequence. If I drop a glass, it shatters. The drop is the cause. The shatter is the effect. The reverse is impossible. But in the quantum realm, that certainty melts away. The experiment that explores this is called the quantum switch. Imagine you have a photon and two processes you can perform on it, let's call them A and B. A regular switch would send the photon through A, then B, or B, then A. A clear, definite order. A quantum switch, on the other hand, uses superposition. A control particle is put into a superposition of two states, 0 and 1. If the control particle is in state 0, the photon goes through A and then B. If the control particle is in state 1, the photon goes through B and then A. But here's the kicker. Because the control particle is in a superposition of 0 and *1, the causal order for the photon becomes indefinite. It exists in a superposition of two different histories. One where A happened before B, and one where B happened before A. A right-pointing arrow B and B right-pointing arrow A are happening at the same time. The experiment doesn't just mix up the results. It creates a genuine quantum superposition of the causal orders themselves. This has been experimentally confirmed. Physicists have shown that nature allows for outcomes that are impossible to explain if you assume A and B happen in any fixed order, even one you don't know. It's not that we don't know the order. It's that there is no definite order. It's a true quantum fuzziness of before and after. Now, we have to be very precise about what this means. This does not mean you can build a time machine and unshatter a broken glass. These are highly controlled experiments on single particles. They're about the weird rules of quantum information, not about reversing events in our macroscopic world. But the implications are stunning. Indefinite causal order isn't just a party trick, it's a resource. It's been shown theoretically that using a quantum switch could give you an edge in certain computing and communication tasks. For example, you could send information through two completely scrambled communication channels that would normally destroy any message. But by putting them in a superposition of orders, some information can get through. This suggests indefinite causality is a real, physical thing that can be harnessed. This discovery forces us to refine our idea of causality yet again. If the quantum world allows a right-pointing arrow B and B right-pointing arrow A to exist in a superposition, then causality can't fundamentally be about a fixed sequence. This adds even more weight to the idea of structural or logical dependence. In an indefinite causal order, the final state of the photon depends on both A and B, but the hierarchy which one is the cause and which is the effect is itself in a quantum superposition. Think back to the house of cards. Now imagine two cards leaning against each other. Which one is holding the other up? You can't say. Their stability is a mutual, codependent relationship. Indefinite causal order is the quantum version of this. It's a state of causal ambiguity. These experiments are the final nail in the coffin for our simple, intuitive notion of time-ordered cause and effect. They show that even the asterisk direction of causality can be a quantum variable. They suggest that at the deepest level, the links between events aren't simple arrows pointing from past to future, but a complex web where the direction of influence can itself be undefined. We're left with a picture of reality far stranger than we started with. At the quantum level, particles exist in a timeless blur. At the cosmic level, the whole universe might be a static object. And at the information level, even the order of cause and effect can be put into a superposition. The simple timeline we live by seems to be a convenient fiction, a useful approximation our brains evolved to navigate our corner of the universe. But it is not the fundamental truth. We've traveled to the very edge of physics, to a place where time dissolves and causality gets weird. We've talked about superposition, timeless universes, and cause and effect happening in both directions at once. So I have to ask you, which of these ideas messes with your head the most? The idea that time is an illusion? Or the idea that an effect can be in a superposition with its cause? Let me know in the comments below. And if you want to keep exploring the absolute frontier of science and what it tells us about reality, make sure you subscribe and hit that notification bell. These are the conversations that push the boundaries of what we think we know, and there's so much more to explore. Rebuilding causality. So let's circle back to that title. Quantum physics just disproved cause and effect. As we've seen, that statement is both wrong and right. It's wrong because causality, the idea that events are linked and depend on each other, is still standing. In fact, it might be even more fundamental than we ever thought. But the statement is also right, because the simple version of causality we use every day, the one that needs a straight, flowing river of time with a clear before and after, has been completely shattered. Quantum mechanics didn't kill causality. It liberated it from the tyranny of time. We saw this first in the quantum realm, where a particle explores all paths at once, and a tunneling particle makes a leap without a journey. There, causality is about the timeless math of the wave function, not a story unfolding second by second. We then saw how this could scale up to the entire universe. In a timeless cosmology like Julian Barber's, or the entanglement model of Page and Wooter's, our experience of past, present, and future emerges from a reality that is fundamentally static. Causality becomes structural. It's the logic of the universe's design, creating an asterisk arrow of time without needing an asterisk flow of time. And finally, experiments with indefinite causal order showed us the most radical idea of all. That the very direction of cause and effect can be put into a quantum superposition. So where does that leave us? With a universe that is far stranger and more interconnected than our intuition can handle. The cozy illusion of a universal clock ticking away has been replaced by a static block of spacetime. And now, even the clear ordering of events within that block is being questioned. Our perception of a straight line of cause and effect is likely an emergent thing, a product of our large scale, our environment, and the way our brains create stories to make sense of the world. We experience the grand sculpture of reality by walking past it, seeing one piece at a time, and creating a narrative of before and after. But the physics is telling us the entire sculpture is already there, existing in a timeless, interconnected whole. Did quantum physics disprove cause and effect? No. It showed us that causality is a principle so fundamental that it doesn't need the crutch of a ticking clock. The universe doesn't need a before to have an after. It just needs its structure to be logical. The timeline we live by might just be a shadow, cast by a reality that is, and always has been, timeless. The secret warm-up lap before our universe began. When you think about the beginning of the universe, what comes to mind? For most of us, it's the Big Bang. A single, explosive moment that created everything from nothing. A point of infinite heat and density, erupting in a silent, cosmic cataclysm. For decades, this has been page 1 of our cosmic storybook. It's the official beginning. But what if that's not the real beginning? What if the Big Bang wasn't the starting line, but just the moment the race officially began? Today, evidence points to a secret, warm-up lap, a mysterious, hidden phase that happened before our universe as we know it even existed. A period of such unimaginable violence and speed that it makes the Big Bang itself look like a gentle afterglow. This isn't just a quirky thought experiment. This is the frontier of cosmology, where scientists are piecing together clues from the oldest light in the universe to uncover a prologue that rewrites our entire understanding of creation. We're going to look at the plot holes in our standard story, uncover the breathtaking theory that seems to fix them, and explore the mind-bending implications of a universe that may not have had a single, definitive start. So get ready to have your idea of reality stretched. The flawed starting line. So, why did scientists even start looking for a before? To get that, we need to understand what the standard Big Bang theory really says and more importantly, what it doesn't. Let's rewind the clock. All the way back. About 13.8 billion years. Our entire observable universe, every galaxy, every star, every atom in your body was squeezed into a region of unimaginable heat and density. And here's the first thing most people get wrong. This was not an explosion in space, like a bomb in an empty room. It was an explosion of space itself. Every point started expanding away from every other point, all at once. There was no center and no outside. The universe wasn't expanding into anything, there was just more universe, appearing everywhere. In the very first moments, the universe was a chaotic soup of particles and energy. In the first microsecond, quarks and gluons swirled in a plasma hotter than a trillion suns. A few minutes later, the universe cooled enough for the first atomic nuclei to form mostly hydrogen and helium. But it was still an opaque, glowing fog. Light was trapped, constantly scattering off electrons like a pinball in a cosmic arcade machine. For 380,000 years, this was the state of the cosmos. Then, a tipping point. The universe cooled enough for electrons to be captured by nuclei, forming the first stable atoms. And just like that, the fog cleared. Photons, particles of light, were set free. For the first time, light could travel across the vastness of space. That first light is still traveling today. We call it the cosmic microwave background, or CMB. When we point our telescopes in any direction, past all the stars and galaxies, we see this faint, persistent glow. It's the oldest light in the universe, a baby picture of the cosmos, and the most important piece of evidence for the Big Bang. Telescopes like the Planck satellite have studied this glow in stunning detail, and it confirms the Big Bang model with breathtaking accuracy. It tells us the universe's age, its expansion rate, and what it's made of. The standard Big Bang theory is a monumental achievement. It's correct. But it's not the whole story. When cosmologists looked closer at this beautiful picture, they found a few deep, nagging puzzles. Not small details, but profound cracks in the foundation of the theory, hinting that a huge part of the story was missing. The first is the horizon problem. Think back to that baby picture of the universe, the CMB. The most stunning thing about it is how freakishly uniform it is. If you measure the temperature of this ancient light from one side of the sky and then from the complete opposite side, they're the same. Not just similar, but the same down to about 1 part in 100,000. Now, why is that a problem? Imagine putting 2 ice cubes at opposite ends of a giant, galaxy-sized oven and turning it on. A few minutes later, you check their temperature. You'd expect them to be different. Heat simply hasn't had time to travel from one side to the other and even things out. For them to reach the exact same temperature, they need time to be in thermal contact, time for heat to flow between them. Our universe is the same. When we look at opposite sides of the sky in the CMB, we're seeing 2 regions that, in the standard model, were never in causal contact. They were too far apart for light, or any information, to have ever traveled between them in the 380,000 years the universe had existed. They never had the chance to talk to each other and settle at the same temperature. And yet, they're the same. It's like finding 2 people on opposite sides of the Earth who have never met, but are wearing the exact same custom-tailored outfit. It defies logic. The standard Big Bang theory has no answer. It just has to assume the universe started that way. That's not an explanation. This alone was a big enough crack to make physicists uncomfortable. But there was another, called the flatness problem. According to Einstein's general relativity, the stuff in the universe, matter and energy, curves the fabric of spacetime. The overall shape of the universe depends on its total density. There are 3 basic options: closed, like a sphere; open, like a saddle; or perfectly flat. Here's the wild part. All our measurements show that our universe is astonishingly, ridiculously flat. Its density is so close to the critical value needed for flatness that it's like measuring the diameter of the observable universe and finding it accurate to within the width of a human hair. Why is this a problem? Because a flat universe is an incredibly unstable state, like a pencil balanced perfectly on its point. Any tiny deviation from perfect flatness at the beginning would have been magnified exponentially over 13.8 billion years. For our universe to be so flat today, its density in the first moments had to be fine-tuned to the critical value to a mind-boggling degree of precision, something like 1 part in 10 to the 60th power. Again, the standard Big Bang model has no explanation. It just says the universe started out flat. That's not a reason, it's an admission that something is missing. These 2 giant cosmic coincidences, a perfectly uniform temperature and a perfectly flat geometry, demanded a better answer. It was clear something must have happened before the hot, dense state we call the Big Bang. Something had to set the stage. There must have been a warm-up lap. The warm-up lap. And this is where the story gets really wild. In the late 1970s and early 80s, a young physicist named Alan Guth was wrestling with these problems and stumbled upon an idea. It was radical, it was bizarre, and it would come to be known as cosmic inflation. Inflation theory proposes that in the very first fraction of a second before the hot Big Bang, we know the universe underwent a period of violent, exponential expansion. Let that sink in. Exponential. It didn't just grow. It doubled, and doubled, and doubled again. In a tiny sliver of time, maybe from 10 to the minus 36 to 10 to the minus 32 seconds, the universe increased in size by a factor of at least 10 to the 26th power, and probably much, much more. A region of space far smaller than a proton was stretched to be larger than our entire observable universe is today. What could drive such a bonkers expansion? The theory suggests a new type of field, the inflaton field, permeated all of space, loaded with energy. This energy had a unique property. It created a repulsive gravity. It pushed everything apart. The more space it created, the more of this energy there was, which in turn created more space even faster. It was a runaway feedback loop of hyper-expansion. This one idea solves the Big Bang's biggest problems with stunning elegance. First, the flatness problem. Remember the pencil balanced on its tip? Inflation changes the game. Imagine an ant on a tiny, crumpled balloon. The surface is obviously curved. Now, blow that balloon up to the size of the Earth. From the ant's perspective, its little patch of the world now looks perfectly flat. Inflation does the same thing to spacetime. It takes whatever initial curvature the universe had and stretches it out to such a colossal scale that our observable patch becomes perfectly flat. The flatness of the universe is no longer a mystery. It's a natural consequence of this incredible stretching. And the horizon problem? How did opposite ends of the universe get to the same temperature? Before inflation, the region that would become our entire observable universe was microscopically small, so tiny that all parts of it were in contact. It had plenty of time to even out its temperature, like a cup of coffee cooling to room temperature. It was a tiny, smooth, uniform patch of space. Then, inflation kicked in and stretched that tiny, uniform region to an astronomical size. The 2 points now on opposite horizons of our sky were once next-door neighbors. They have the same temperature because they were at the same temperature before inflation ripped them apart. But inflation does more than just solve old problems. It makes a new, unique, and testable prediction. According to quantum mechanics, the vacuum of space isn't empty. It's a fizzing sea of quantum fluctuations. During inflation, these microscopic jitters were stretched out along with space itself, magnifying them to cosmic proportions. These magnified fluctuations created tiny differences in density from place to place. And here's the smoking gun. Inflation predicts a very specific, nearly scale-invariant, pattern for these fluctuations. Fast forward. After inflation ends, these tiny density differences act as cosmic seeds. Slightly denser regions have slightly stronger gravity, pulling in more matter over billions of years. These are the seeds that grow into galaxies, stars, and ultimately, us. The theory predicts that if we look at the CMB, we should see tiny temperature variations reflecting these seeds, with that specific scale-invariant pattern. In 1992, NASA's COBE satellite did exactly that. It found the tiny temperature fluctuations, just as predicted. Later, the WMAP and Planck satellites measured these fluctuations with incredible precision, confirming the predictions of the simplest inflation models to an astonishing degree. We are literally seeing the fossilized evidence of quantum fluctuations from the first moment of creation, written across the entire sky. This gives us a new timeline. The beginning wasn't a singular point. It was a process. An unknown state gives way to a tiny patch of space beginning to inflate. It expands exponentially, smoothing out wrinkles and seeding the cosmos with the blueprints for galaxies. Then, the warm-up lap ends. Okay, let's take a breath. We just journeyed from the edge of established science into a theory that completely reshapes our cosmic origins. It's a lot to take in. If your mind is buzzing with these ideas as much as mine is, this is probably a good time to subscribe and hit the bell icon. This channel is all about tackling the biggest questions in science, and you won't want to miss what happens when the warm-up lap finally ends and what that means for the existence of other universes. A new cosmic perspective. So, inflation fixed the Big Bang's biggest headaches and made a stunningly successful prediction. But it left us with a new, burning question. If inflation created a universe that was vast, flat, and empty, where did all the asterisk stuff come from? Where did the hot, dense soup of particles that we call the Big Bang originate? The answer lies in the end of inflation. The inflaton field couldn't expand forever. It was in an unstable, high-energy state. At the end of the inflationary epoch, the field decayed, rolling down to its stable, low-energy state. All that incredible energy driving the expansion had to go somewhere. It was converted, in a universe-spanning flash, into a torrent of matter and radiation. This process is called reheating. This is the moment we have traditionally called the Big Bang. Let's be very clear, because this is the central point. The end of inflation is the beginning of the hot Big Bang. The Big Bang wasn't the ultimate origin. It was the consequence of the warm-up lap ending. It was the starting pistol, dumping all the energy from that prep phase into the cosmos, kicking off the marathon we see today. The hot, dense state wasn't the beginning, it was the result of reheating. This completely reframes our picture of creation. There was no singularity as we used to imagine it. The physics of inflation, while extreme, remained finite and describable. Inflation takes the idea of an infinitely dense starting point and shoves it back into a past we can't yet access, maybe getting rid of it altogether. But this new picture opens a Pandora's box of new possibilities, the most mind-bending of which is called eternal inflation. Those quantum fluctuations didn't just seed galaxies, they also affected the inflaton field itself. In some places, they would help the field decay, ending inflation and starting a Big Bang. But in other places, the quantum jitters could be strong enough to keep inflation going. According to leading models, this process is unavoidable. While inflation ends in some patches of space, there will always be other patches where it continues. And since those inflating regions are expanding exponentially, they will always dominate. Inflation, once it starts, may never completely stop. It becomes eternal. What does this mean? It means our universe might just be one bubble, one pocket universe in a vast, eternally inflating metaspace, like a bubble forming in a boiling pot of water. And our bubble isn't the only one. Far beyond our horizon, other Big Bangs are constantly firing, spawning an infinite number of pocket universes. A multiverse. This isn't just a wild guess. For many physicists, it's the most logical, if unsettling, consequence of inflation. It suggests universe creation is happening all the time. These other bubble universes could be wildly different, with different particles and forces. Some might be stillborn, while others expand too fast for stars to form. But in an infinite sea of possibilities, some would have just the right conditions for complexity, for planets, and for life. This offers a potential solution to another deep mystery. Why are the laws of our universe so perfectly suited for us? Well, if there are infinite universes, we simply find ourselves in one where we could exist. But if inflation is eternal into the future, a question immediately arises. Was it eternal in the past? Did the multiverse always exist? Here, we reach the absolute frontier of knowledge. In 2003, three physicists Arvind Borde, Alan Guth, and Alexander Vilenkin developed a powerful mathematical theorem. The BGV theorem is remarkably general. Its conclusion is profound. Any universe that has, on average, been expanding throughout its history cannot be infinite in the past. It must have a beginning. Even an eternally inflating multiverse. As Vilenkin himself puts it, we have to face the problem of a cosmic beginning. The BGV theorem shows that while inflation could go on forever into the future, it can't have been going on forever in the past. It, too, must have started. So what came before inflation? What was the state of things at the beginning? Demanded by the BGV theorem. This is the question that consumes modern theoretical physics. We don't have an answer. We have speculative ideas, tantalizing math, but no solid theory. One idea is a big bounce, where a previous universe collapsed and bounced into our own. Another comes from string theory, where our universe is a brane that collided with another in a higher dimension. A third is a true creation from nothing, in a quantum mechanical sense, where time itself emerged along with the universe. These ideas are at the very edge of what we can imagine, let alone test. They require a theory we don't have yet, a complete theory of quantum gravity. What's clear, however, is that our cosmic story is far richer and stranger than we once believed. The simple picture of a single Big Bang has given way to a multi-layered saga. A pre-cosmic state, the start of inflation, a violent warm-up lap, a blaze of reheating that kicks off the hot Big Bang, and 8 billion years of evolution, all of which may be just one bubble in an infinite cosmic ocean. So, where does that leave us? We started by asking a simple question. What came before the Big Bang? We saw that the classic story, as great as it is, had some serious plot holes. The horizon and flatness problems. The solution we found was cosmic inflation, a secret warm-up lap before the hot Big Bang that set the stage for everything. It's a theory that not only solves old puzzles but made predictions confirmed by the oldest light in the universe, telling us that the grand tapestry of galaxies is the macroscopic echo of microscopic quantum jitters. But this new understanding doesn't give us a final answer. It deepens the mystery. It points to a multiverse of infinite possibilities. And yet, even this grand multiverse cannot be eternal into the past. It, too, must have had a beginning. So the Big Bang wasn't the absolute starting line. It was the moment the race officially kicked off, powered by the end of the warm-up lap. But that warm-up lap itself had a beginning, a boundary we cannot yet cross. We have pushed back our ignorance from 8 billion years ago to a mere fraction of a second after whatever came first. But the ultimate origin, the true time equals zero, remains hidden, waiting for the next revolution in our understanding. Our universe did not simply explode into being. It seems to have emerged from a process far more complex, mysterious, and magnificent than we ever dared to imagine. Finding that ultimate beginning is the greatest detective story of all time. And the investigation has only just begun. The universe's slow fade into eternal darkness. This isn't a story about a bang. We've had that already. This is a story about the final, long, drawn-out whisper. It's a journey to a time so far away that the very idea of time starts to unravel and lose all meaning. A journey to a future where the last star has flickered out, every galaxy has dissolved into dust, and the universe is nothing but a cold, dark, and eternally still void. Can you picture it? Drifting in an endless, silent blackness where the only thing that exists is the ghost of what used to be. There are no explosions here, no cosmic collisions, just a slow, patient, and unavoidable fade into nothing. This is the story of the universe's final act. So, what does the end of everything actually look like? The answer is quieter, stranger, and more profound than any disaster you could ever dream up. Let's take a walk to the very edge of existence. The universe as we know it, a fleeting moment of light. Right now, you and I are living in a bonfire of creation. We exist in a fleeting, brilliant era that cosmologists call the stelliferous era, the age of stars. When you look up at the night sky, you're seeing the universe at its peak. It's a cosmic engine, humming with furious activity. Stars are giant fusion reactors, turning hydrogen into helium and bathing their planets in life-giving light and heat. Galaxies, those incredible spinning islands of stars, are still close enough to see each other, dancing through the void. From swirling gas clouds in nebulae, new stars and new worlds are being born as we speak. This is a universe that's teeming with light, with energy, with difference. And that idea of difference is the key to, well, everything. Our universe is a place of amazing gradients. You have incredibly hot stars right next to the freezing cold of empty space. You have unbelievably dense planets surrounded by a near-perfect vacuum. This is all possible because the universe began in what physicists call a state of low entropy. Entropy is just a measure of disorder or uniformity. A low-entropy system is ordered and full of potential. Think of a hot cup of coffee in a cool room. That temperature difference is a gradient, and it allows energy to flow. The coffee cools down as it warms the air. That flow is what lets work happen. It's what drives every engine, every chemical reaction, and every biological process, from a star going supernova to the synapses firing in your brain as you listen to these words. Our universe, right now, is that hot cup of coffee, a pocket of concentrated order and energy in the vast, cold room of spacetime. But there's a fundamental rule of our reality, a law so ironclad it's considered the most unbreakable principle in physics. The second law of thermodynamics. It says, simply, that in a closed system, entropy disorder always increases over time. That hot coffee will never get hotter on its own by stealing heat from the cool room. A scrambled egg will never unscramble itself. The universe, as a whole, is a closed system. And so, it's relentlessly shuffling itself toward a state of ultimate, perfect disorder. This cosmic shuffle is being pushed along by two forces we can't escape. The first is simple. Stars are burning through their fuel, radiating their energy out into the void, never to be used again. The second is a much more mysterious and powerful force we've only recently discovered: dark energy. This strange pressure, woven into the fabric of spacetime itself, is making the universe expand faster and faster. It's pushing galaxies away from each other at an ever-increasing speed. The second law of thermodynamics wrote the script for our universe's end, and dark energy is the engine driving us toward that final, inevitable scene. We're living in a brief, glorious age of light, but the shadows are already starting to creep in. The fade has already begun. The first shadows fall. The end of the stelliferous era. Our trip into the far future starts with events that, on a cosmic scale, are practically right around the corner. In about 5 billion years, our own star, the Sun, will start to die. Once it's used up the hydrogen in its core, the balance between gravity and energy will break. It will swell into a red giant, its outer layers expanding to swallow Mercury, Venus, and perhaps even the Earth. Our world's fate isn't sealed as the Sun loses mass, its gravitational pull will weaken, and Earth's orbit might expand just enough to escape being consumed. But even if it does, the planet will be scorched into a lifeless rock. After this dramatic phase, the Sun will shed its outer layers, and its core will collapse into a tiny, super-dense, Earth-sized ember called a white dwarf, destined to cool and fade for trillions of years. Around the same time, our cosmic neighborhood will get a major makeover. The Andromeda Galaxy, our biggest galactic neighbor, is currently hurtling toward our Milky Way at hundreds of thousands of miles per hour. In about 4 to 5 billion years, they'll collide and merge. This won't be a violent crash, but a slow, majestic gravitational dance that will take hundreds of millions of years. The two spiral galaxies will pull each other apart and eventually settle into a new, giant elliptical galaxy that some have nicknamed Milkomeda. Now, let's fast forward, way beyond these local dramas. Let's go to 100 trillion years from now. At this point, the universe looks profoundly different. The unstoppable expansion from dark energy has pushed all other galaxies so far away that their light will never reach us again. The sky outside our own giant, merged galaxy will be a featureless, inky black. More importantly, the universe will have run out of the raw materials for creation. Star formation will have pretty much stopped. The huge clouds of gas and dust that form stellar nurseries will have been used up or spread so thin they can't collapse to make new stars. The universe's era of birth is over. Now, only decay remains. The only stars left will be the most frugal ones in the cosmos, red dwarfs. These small, dim stars sip their hydrogen fuel so slowly they can last for trillions of years. For an immense period of time, they will be the only lights left. Imagine a galaxy lit not by brilliant blues and whites, but by the faint, dull red glow of dying embers. But even they can't last forever. One by one, over trillions more years, the last red dwarfs will finally burn out, flicker, and die, collapsing into white dwarfs. And then, a moment will come. The very last star in the universe will go dark. From this point on, the cosmos will be plunged into a darkness that will last for an eternity we can barely wrap our minds around. The stelliferous era is over. The lights are out. The degenerate era, an empire of corpses. Welcome to the degenerate era. The name sounds bleak, but it's a perfect technical description of what the universe has become. The age of stars is a distant memory, and what's left is an empire of stellar corpses. The universe is now filled with degenerate matter, the crushed, compacted remains of once great suns. There are white dwarfs, the size of planets with the mass of stars. Neutron stars, the size of cities but more massive than our sun, so dense a single teaspoon would weigh billions of tons. And black holes, points of infinite density where gravity is so powerful that nothing, not even light, can escape. These are the new residents of the cosmos, scattered like tombstones in a dark, silent, and ever-expanding graveyard. The grand structures we know today will be gone. Over unimaginable eons, the graceful dance of stars in their galaxies will fall apart. Gravitational interactions will act like a cosmic slingshot, flinging most of these stellar remnants out of their host galaxies and into the lonely void. The few that remain will spiral inward, toward the supermassive black hole at the galaxy's center. The majestic arms of the Milky Way, the sprawling city of Milkomeda, all will dissolve into a scattered, chaotic cloud of drifting embers. But even these stellar corpses aren't forever. The universe is about to get even stranger, thanks to a deeply compelling, though still unproven, idea from particle physics. Proton decay. Protons are the building blocks of the matter we know. According to the standard model of physics, the theory that describes the forces and particles of our universe, protons are perfectly stable and last forever. But many theories that try to go beyond the standard model, known as grand unified theories, predict that this isn't true. They suggest that over immense timescales, protons can decay, transforming into a puff of lighter particles and radiation. This isn't a fast process. Experiments searching for proton decay at facilities like Japan's Super Kamiokande Observatory haven't found any yet, which tells us that if protons do decay, their half-life is incredibly long, at least 10 to the power of 34 years. That's a number so big the entire age of the universe is just a blink by comparison. But in the patient timeline of the degenerate era, there's plenty of time. If proton decay is real, then everything we consider matter will slowly, but surely, evaporate. Picture a white dwarf, a planet-sized diamond of crystallized carbon and oxygen. Over trillions of millennia, it would simply fizz away, atom by atom. A neutron star would dissolve. Planets, asteroids, dust, all of it would unravel. Matter itself would be erased from existence, its very substance converted into a faint mist of radiation. This is the ultimate decay, a slow sublimation of the physical world. After an almost infinite amount of time, the only structured things left will be the ones not made of normal matter. The only things left will be the black holes. The black hole era, the last titans. We've now jumped into an age so remote it beggars belief, maybe 10 to the power of 40 years in the future. The degenerate era is over. All matter made of protons and neutrons has decayed, leaving behind a thin, featureless soup of photons and other stray particles. The universe is almost perfectly empty and dark. Almost. Presiding over this enormous void are the last titans, black holes. This is the black hole era. Having grown to colossal sizes by swallowing the stars and gas from their long-dissolved galaxies, these supermassive black holes are the last complex objects in the universe. They are silent monarchs reigning over an empire of nothing. For an immense stretch of time, it would seem that this is the end, a universe dotted with eternal prisons of spacetime. But in 1974, Stephen Hawking made a discovery that changed our understanding of forever. By blending general relativity and quantum mechanics, he showed that black holes aren't completely black. They aren't eternal. They leak. The process is called Hawking radiation. Quantum physics tells us that even empty space is a fizzing foam of virtual particles that pop into existence and then annihilate each other in a flash. But right at the edge of a black hole's event horizon, the point of no return, one particle can fall in while the other escapes. From the outside, it looks like the black hole just spat out a particle. This carries away a tiny bit of energy, which, thanks to E equals mc squared, means the black hole loses a tiny bit of mass. It's evaporating. The process is excruciatingly, painfully slow. For a black hole the mass of our Sun, it would take around 10 to the power of 67 years to evaporate. For the supermassive black holes that once sat at the heart of galaxies, the timescale is even more staggering, up to a Google years, or 10 to the power of 100. Let's go to that final moment. The universe is a vast, cold void, with just a few last, lonely black holes. For a Google years, the very last and largest of them all has been slowly leaking its mass away as a faint glow of Hawking radiation. As it gets smaller, the evaporation speeds up. In its final moments, its temperature skyrockets. And then, in one last, quiet flash of high-energy radiation that lights up the void for a split second, the last black hole evaporates completely. The last complex structure in the universe is gone. The black hole era is over. The dark era, eternal stillness and the death of time. We've finally arrived. This is the final age of the universe, the dark era. The last star has been dead for trillions of years. The last matter has dissolved. The last black hole has vanished. What's left? The universe is now a vast, endlessly expanding, and unimaginably thin soup of particles. A faint gruel of photons, neutrinos, and other elementary particles drifts through the void, separated by incomprehensible distances. The temperature has dropped so close to absolute zero it's practically indistinguishable. This is the state of maximum entropy. Thermodynamic equilibrium. The hot coffee has finally reached room temperature. All the gradients, all the differences in energy that drove every single process in the universe, are gone. Nothing happens. Nothing can happen. And here, at this final frontier, we have to ask the deepest question. What happened to time itself? The way we experience it, time has a direction. It flows forward. This arrow of time is tied directly to entropy. Time moves from a state of low entropy, an ordered, unbroken egg, to one of high entropy, a disordered, scrambled egg. The second law of thermodynamics is the reason you can't unscramble an egg, and it's what gives time its forward momentum. But what happens when entropy can't increase anymore? In a universe at maximum entropy and perfect equilibrium, the arrow of time has no direction. As cosmologist Dr. Katie Mack puts it, the second law of thermodynamics doesn't know which direction the future is. There's no meaningful before or after, because every moment is statistically identical to the last. Without change, without anything happening, does time even exist? This is the concept of heat death. Not a fiery end, but the death of heat itself, the end of all difference. Particles might still move, but on any meaningful scale, the universe is frozen in a state of eternal stillness. No clocks can tick because there is no change to measure. Time hasn't so much stopped as it has become irrelevant. The universe has entered a state of timelessness, an endless, silent, and thoughtless expanse of near-nothingness, stretching on for an eternity that has lost all meaning. This is the most likely end to our cosmic story. A slow fade into a perfect, quiet dark. An alternate ending? Whispers of a big crunch. But what if the story doesn't end with a whisper? For decades, the heat death has been the consensus, driven by the idea that dark energy is a constant force, always pushing things apart. But in cosmology, there are always other ideas, and some recent hints suggest a much more dramatic finale. It all comes down to the true nature of dark energy. What if it's not a constant? What if it's a dynamic field, something called quintessence, that can change over time? If dark energy can change, its repulsive force might not be permanent. It could weaken. It might even flip. This is the revival of the Big Crunch scenario. While still speculative, some recent analyses of data from major surveys like the Dark Energy Spectroscopic Instrument, (DESI), have shown that models where dark energy fades over time can fit our observations. If this is true, the accelerating expansion of the universe could slow down, stop, and then catastrophically reverse. In that version of the future, gravity would once again become the dominant force. Galaxies would stop flying apart and start falling back together. The universe would begin to contract. As it shrinks, it would get hotter and denser. Galaxies would merge, stars would collide, and the background radiation would heat up from near absolute zero to a raging inferno. In the final moments, the entire cosmos would collapse back into an infinitely hot, infinitely dense singularity, the same state from which it all began in the Big Bang. It's important to stress that this is still a long shot. The bulk of the evidence points toward eternal expansion and heat death. But these alternate models are a powerful reminder that we don't have all the answers. The mystery of dark energy is the biggest unknown in our cosmic forecast, and until we solve it, the final chapter of the universe hasn't been definitively written. We've journeyed from the vibrant, star-filled cosmos of today to the edge of eternal darkness, and even considered a fiery return to the beginning. These are the biggest questions we can ask, stretching our minds to their absolute limits. If these kinds of cosmic explorations fascinate you, consider subscribing and joining our community of explorers. And after all that, I'm curious, what part of the universe's end do you find the most mind-bending? The silent decay of all matter, the evaporation of black holes, or the idea of time itself losing its meaning? Let me know in the comments. I'd love to read your thoughts. A fleeting, precious light. We have stared into the abyss. We've contemplated a future of unimaginable cold and darkness, a final state where the universe itself forgets the passage of time. It's a humbling vision, one that can make our own existence feel impossibly small. But that's the wrong way to look at it. The real takeaway here isn't the coming darkness, but the incredible preciousness of the light. The story of the universe's end is what gives profound meaning to right now. We are living in the cosmic dawn, the brief, glorious, incandescent chapter of the universe's life. We are here, now, in the stelliferous era, a time when there is enough energy and complexity for galaxies to spin, stars to shine, planets to form, and for life to look up at the sky in wonder. The ultimate coldness of the future doesn't make our present warmth meaningless. It makes it miraculous. We are the universe's way of witnessing itself, of thinking about itself, of appreciating its own fleeting beauty before the long night falls. Knowing that all of this will eventually fade away doesn't have to be a source of despair. It can be a powerful call to appreciate the here and now. To appreciate the light, the warmth, and the brief, extraordinary moment we get to be a part of. The final darkness is the backdrop that makes the light of our existence shine so brilliantly. Science proves you can witness the end of time. Picture this. You're adrift in the deepest, darkest void of space. Your ship is a ghost, its engines have been silent for an age. The stars, which used to warp past your window in brilliant streaks, have stopped their frantic dance. Now, they're just frozen. Perfect, crystal clear points of light hanging in an endless, unblinking stillness. The light from all around you doesn't just get dim. It stops. Everything stops. You've reached it. A frontier more terrifying and more profound than any place you can point to on a map. You are hovering on the razor-thin edge where time itself bleeds into timelessness. So, what happens now? What happens if you, the one who is watching, the observer at the end of everything, decide to cross that line? This isn't some distant, philosophical, maybe. We're talking about what cutting-edge physics says is a real consequence of our universe's deepest laws. We're about to explore that mind-bending boundary, how your own perception would slow to a crawl, how the entire cosmos could lock itself into a perfect, eternal freeze frame, and maybe the most startling idea of all. Why you, the person watching, might be the secret key to the whole thing. By the end of this, you'll see that this isn't just a wild theory, it's the ultimate cosmic cliffhanger. What if I told you that the most basic aspect of your reality, the steady march of moments from past to future, is a lie? Not a misunderstanding. Not a metaphor. A complete illusion. It feels real, doesn't it? The tick of a clock, the beat of your own heart, the memory of what you did yesterday and the hope for tomorrow. This is the bedrock of how we experience life. And yet, for decades, a quiet revolution has been brewing in physics, and its conclusion is as inescapable as it is shocking. Time doesn't exist. At least, not in the way any of us think it does. Our best theories of the universe, the ones trying to connect the massive scale of gravity with the strange rules of the quantum world, all seem to point to the same unnerving idea. Time isn't some fundamental river flowing through the cosmos. It's not a universal clock ticking away for everyone, everywhere. Instead, modern physics suggests that time is an asterisk emergent property. It's something that arises from a deeper, static, and totally timeless reality, kind of like how the feeling of hot or cold emerges from the chaotic motion of atoms, or how a moving picture on a screen emerges from a static grid of pixels. This isn't just philosophers kicking back in their armchairs. This is a real problem that pops up when we try to write down the ultimate equation of reality. In this script, we're going on a journey to the very foundation of that reality. We're going to ask, and try to answer, some pretty radical questions. First, what is this boundary between time and timelessness? Where does the illusion of flow come from, and where does it all break down? Second, what would happen to you, a conscious observer, as you got close to this edge? Would your perception, your own consciousness, actually slow down as the universal clock unwinds? Third, what would the universe even look like from there? Would it really be frozen, like a static photograph of a single moment held for eternity? And finally, we'll tackle the biggest twist in this whole story. What is the observer's role in all this? As we're about to see, you're not just a passive passenger along for the ride. You are, in a very real sense, a part of the engine. Prepare to have your understanding of existence rewired. We're about to show that you can, in principle, witness the end of time. Because in a way, you're the one who helps define its beginning. The disappearing act of time. To even think about a journey to the end of time, we have to first break down our most deeply held belief. That time is real and it only flows one way. We feel this as the arrow of time. A glass falls and shatters, but we never see the pieces fly back together to form a glass. We remember the past, but not the future. This one-way street feels absolute. For a long time, physicists thought this arrow was all about entropy, the universe's unstoppable slide from order into disorder. The Big Bang started in a very low entropy, highly ordered state, like a perfectly wound-up clock. The history of the universe is just that clock unwinding into a more chaotic, high-entropy state. So, the arrow of time is really just the arrow of increasing entropy. But what if that only describes what's happening inside the illusion, and isn't the source of the illusion itself? What if the ideas of before and after are the real mirage? This is where physics presents a truly radical idea: the block universe. Try to imagine the entire history of the cosmos from the Big Bang to the last dying star not as a story that's unfolding, but as a single, finished object. Think of it like a movie on a DVD. The whole story, beginning, middle, and end, exists all at once on that disc. Your life, the life of Julius Caesar, the birth of our sun, and its eventual death aren't events that happen and then disappear. They are all just different locations inside this four-dimensional block of spacetime. In this model, the past, present, and future are all equally real. That feeling you have of being in the present is just that, a feeling. It's a subjective experience based on your specific location within the block. Your future self, living out there, present, moment years from now, is just as real as the you watching this right now. This isn't just sci-fi, it's a direct consequence of Einstein's theory of relativity. Relativity shows us there's no such thing as a universal now. Two people moving at different speeds can disagree on which events are happening simultaneously. And if there's no universal now, then maybe all moments are equally real, all coexisting forever inside the block. But even the block universe still has time as one of its dimensions. The real revolution, the final vanishing act, happens when we go deeper, down to the quantum level. In the 1960s, physicists John Wheeler and Bryce DeWitt tried to smash general relativity and quantum mechanics together to create a single theory of everything. They came up with the Wheeler-DeWitt equation, which is supposed to describe the quantum state of the entire universe. And when they looked at what they'd made, they found something deeply weird. The variable for time, the little letter t, that's in almost every other physics equation, was just gone. Let that sink in. The most fundamental equation we have to describe the whole cosmos is timeless. It doesn't describe a universe that changes in time. It describes a static, frozen, unchanging reality. This is famously called the problem of time in physics. Our two greatest theories just can't agree on what time is. For quantum mechanics, time is like a rigid background clock. For relativity, it's a bendy, flexible fabric. When you try to merge them, time just cancels itself out. The universe, from this God's eye view, is frozen solid. So how do we get from a frozen cosmos back to the moving, breathing world we experience? This is where the work of physicist Julian Barbour comes in with a beautiful, if brain-melting, solution. Barbour says we should take the timelessness of the Wheeler-DeWitt equation seriously. He argues that time, as a flowing river, simply doesn't exist. Instead, what's real is an infinite collection of nows. Imagine a huge, multi-dimensional landscape. Barbour calls this Platonia. Every single point in this landscape represents one possible arrangement of the entire universe, a single, static snapshot, or a now. There's a point that represents the universe with you watching this video. There's another point for the universe a moment ago, with your eyes a few words back on the screen. There are other points for dinosaurs roaming the earth. There is no river of time connecting them. There's just this infinite collection of individual, static, timeless snapshots. So where does the asterisk feeling of time come from? Barbour's genius was realizing that what we think of as the flow of time is really just a journey our consciousness takes through this landscape, stepping from one now to the next, like we're flipping through the pages of a cosmic flipbook. And what guides this journey? A simple rule. The universe seems to move toward greater complexity. In this view, the Big Bang wasn't an explosion at the beginning of time. It's a special point in this landscape of nows, a point of maximum simplicity. From that simple starting point, endless paths lead upwards toward more complex and structured arrangements. Our brains are hardwired to interpret this sequence of ever more complex nows as a straight line. We find records in each now, memories in our brains, fossils in the ground, light from distant stars that all point back to a simpler past. These records create the powerful illusion that time has flowed from that past to our more complex present. But in reality, there are only the nows. And this changes everything. Because if time is just an illusion born from a path through a timeless landscape, it means there must be a place where that path begins, a boundary where the illusion is born. And if it can be born, it can be visited. You, the time traveler at the brink. The idea of a timeless universe is one thing. But the idea that you could actually approach its edge is where this turns from a physics lecture into a deeply personal, mind-bending thought experiment. To understand what would happen to your perception, we have to zoom way in, from the scale of the cosmos down to the quantum mechanics happening inside your own brain. First, let's rethink what a clock is. A clock isn't just something on the wall. Anything that changes in a regular, measurable way can be a clock. Your heartbeat is a clock. The firing of neurons in your brain is a clock. The decay of a radioactive atom is a clock. In the 1980s, physicists Don Page and William Wouters came up with a revolutionary idea about this. They suggested that time, as we feel it, emerges from quantum entanglement. Imagine that static, timeless universe from the Wheeler-DeWitt equation. Now, let's split it into two parts. A clock, like the atoms in your brain, and the rest of the universe. The Page-Wouters idea is that for someone inside the system, the universe seems to evolve because the state of their internal clock is entangled with the state of everything else. As the clock ticks, the corresponding state of the universe appears. It's like two sides of a quantum coin that are forever linked. For us on the inside, the entanglement between our personal clocks and the cosmos creates the dynamic show of reality. Someone looking at our universe from the outside would see nothing but a static, unchanging system. This has even been demonstrated in principle in lab settings with simple systems, showing that for particles inside, time emerges, but it's absent from an external point of view. So what makes the clock tick forward and not backward? The answer seems to be a process called quantum decoherence. At the quantum level, a particle can be in many possible states at once, a superposition. It's only when it interacts with its environment, when it's measured or observed, that it collapses into one single, definite state. This interaction and collapse is decoherence. Every time a particle in your brain bumps into another, every time a photon from the outside world hits your eye, a little bit of quantum information leaks out. This constant leaking is what makes the process irreversible. It's like the friction of reality. Decoherence is what forces the fuzzy, probability-driven quantum world to act like the solid, predictable classical world we know, and it's the engine that drives the arrow of time forward. Now, let's put it all together. You're in your ship, heading toward this theoretical boundary of time. In Barber's model, you're navigating through the landscape of nows, back toward that origin point of minimal complexity, the Big Bang. As you get closer, the universe gets simpler. There's less structure, less complexity, less stuff for the quantum bits in your brain to interact with. The process of decoherence, the very engine of your perception of time, would start to sputter. The constant leakage of information that collapses quantum states and creates the flow of moments would slow to a trickle. Your internal clock, which depends on these irreversible interactions, would start to lose its rhythm. The quantum states in your brain would stay in a fuzzy superposition for longer and longer. What would this feel like? It would be the ultimate slowdown. Not like time dilation from moving fast, but something way more fundamental. Your perception itself would begin to stretch. The time between one thought and the next might feel like it's expanding. The duration of a single heartbeat could feel like an eternity. The arrow of time, normally sharpened by countless decoherent events every single nanosecond, would become dull. Its direction would start to fade. And here, we find a tantalizing clue from the real world that hints at this kind of behavior. It comes from the strange world of quantum tunneling, where a particle can pass through a barrier it shouldn't have the energy to cross, like a ghost walking through a wall. For decades, physicists have debated a simple question. How long does it take for the particle to get to the other side? Using incredibly precise atto clocks, experiments have found a stunning answer. For certain particles, the time it takes to tunnel is, within the bounds of measurement, practically zero. While it's still a topic of hot debate, this phenomenon points to something like a timeless leap. The particle disappears from one side and appears on the other, seemingly without any real time passing in between. As you, in our thought experiment, approach the great boundary where decoherence fades away, your own consciousness might begin to experience something similar. Instead of a smooth flow, your perception could become a series of these timeless, instantaneous jumps between different states. The very fabric of your reality would start to unravel, revealing the static, timeless quantum threads underneath. A universe in perfect stillness. As your perception of time stretches and dissolves, what would you actually see looking out your window? What does a universe on the brink of timelessness look like? The answer, according to these theories, is that it wouldn't just be moving in slow motion. It would be utterly and perfectly frozen. Let's go back to that idea of entanglement, where time emerges from the conversation between your internal clock and the rest of the universe. As you approach the boundary of minimal complexity, the conditions that allow for that entanglement start to break down. The conversation between your clock and the cosmos becomes stilted, and the connection weakens. At the ultimate boundary, that entanglement would shatter completely. The moment that happens, the illusion of an evolving universe is over. From your perspective, everything would just stop. You would be staring out at a single, static, now. From Julian Barber's Landscape, a cosmic photograph of one specific arrangement of everything in existence. Distant galaxies wouldn't be expanding away from you. Their light would be frozen in its path. Stars wouldn't be burning. They'd be fixed, unwavering points of light. Nothing would move. Nothing would change. You'd be looking at the raw, unprocessed reality of the block universe, a single slice of it, held in perfect, perpetual stillness. But here's a paradox. If the universe is frozen, how would you even know a past ever existed? You'd see planets, stars, galaxies, all these complex structures that imply a history of development. Julian Barber has a neat answer for this: time capsules. He says that any given now can contain structures that are basically records of a past. A fossil is a record. A crater on the moon is a record. A memory stored in your brain is a record. These records are just arrangements of matter inside that static now that look like they evolved from a simpler state. So, from your viewpoint at the edge of time, you'd see a universe filled with these records. You would see the footprint, but you would never have seen the foot that made it. You'd see the memory, but not the experience that created it. The entire universe would be like a museum of perfectly preserved artifacts, each one telling a story of a dynamic past, but existing in a reality where that dynamism, that flow, has stopped. This leads to an even stranger consequence for the laws of physics. Causality, the familiar chain of cause and effect, would seem to break down. Normally, we see a cause, a bat hits a ball, lead to an effect, the ball flies away. In this frozen now, you only see the final state. You see the universe as a single, self-consistent photograph. It would be a world of effects without causes. You'd be looking at a holographic still life. The logic of reality would flip. Instead of the past determining the present, this single, timeless now would contain all the information of its potential pasts. You wouldn't be watching a movie. You'd be staring at the single frame of film from which every possible prequel could be imagined, but none of them ever actually happened. It is the ultimate stillness, a universe where being has completely won out over becoming. If the idea of a frozen universe and a past that never really happened is bending your mind right now, and you want to keep questioning the fabric of reality with us, do us a huge favor and hit that subscribe button and ring the notification bell. We love falling down these deep, fascinating rabbit holes, and we want you to be here with us for the next one. This whole journey raises a question that gets to the heart of what it means to be, well, us. What do you think? Is time the most real thing there is, or is it the most convincing illusion we've ever encountered? I genuinely want to hear what you think about all this. Let me know in the comments below. The twist. You are the architect of time. We've journeyed to the edge of reality, where time dissolves and the universe freezes. But now we're at the final, most profound revelation, a twist that changes the whole picture. You aren't just a witness to the end of time. In a very real, physical sense, you're a part of what makes it happen in the first place. This whole time, we've been picturing a passive observer, someone looking out a window at the universe. But that's a classical idea, and quantum mechanics threw it out the window a century ago. In the quantum world, there's no such thing as a truly passive observer. The very act of observation, of measurement, of interaction is a creative one. When a particle is in a fuzzy superposition of states, it's the act of measurement that forces it to choose a single reality. The observer doesn't just see which path the particle took. Their interaction is what defines the path. You're not just watching the movie of reality. Your attention is like the light from the projector. It's what makes the images appear on the screen at all. Now, let's apply that idea to Julian Barber's timeless landscape of nows. Without an observer, or more accurately, without a complex system that can create and store records, the entire landscape of possibilities just exists in a giant, simultaneous superposition. All possible nows, all possible configurations of the universe, simply are, all at once, with no story connecting them. There is no flow, no history, no time. But then, you show up. A complex, information processing system we call a conscious observer. By your very nature, your brain processes information in a sequence. You form memories, which are records of a previous state. This very act of forming a record, of interacting with your environment in a way that separates before from after, is a form of measurement. And in that moment of measurement, you collapse the superposition. By having a memory of a simpler now, you are defining a path through that landscape of possibilities. You are tracing a history out of the timeless block. That path is time. Time, in this view, isn't something the universe has. It's something that happens because of the relationship between the universe and a complex subsystem within it. The arrow of time is the trail you leave behind as your consciousness picks its way through the landscape, always moving toward more complexity, because that's the only direction where stable records, like memories, can form. You don't just experience the flow of time. Your existence helps generate it. So, let's ask our final question one last time. What really happens if you, the one tracing the path of time, reach the absolute boundary? The starting point of zero complexity. The answer is the final paradox. The very concept of you, as a single, coherent observer, would dissolve. Remember decoherence? It's what gives you your solid, definite form and separates you from everything else. At that boundary, where interactions stop and complexity vanishes, there is no more decoherence. Your own body and brain would no longer be a classical object. Your quantum wave function, which was once collapsed into the person you call you, would smear back out into a haze of possibilities. There would be no single You left to perceive a frozen universe. Instead, you would merge with the timeless state itself. You would become one with the superposition of all possibilities. You wouldn't see the end of time, you would become timeless. Your perception wouldn't just stop, it would evaporate back into the indifferentiated quantum foam from which reality emerges. The universe, therefore, doesn't freeze for you. It simply reveals its true nature as an always frozen, timeless mathematical object. The grand, sweeping story of cosmic evolution, the flow of billions of years, the drama of stars and galaxies, all of it is a local illusion, a story carved into one small corner of this infinite, static sculpture by the act of observation itself. The boundary isn't a wall you crash into. It's a mirror that shows you the illusion you've been chasing since the first tick of the very first clock. We started this journey with a wild question. Can you witness the end of time? We've traveled from the comfort of a ticking clock to the mind-bending frontiers of quantum gravity, and the answer we've found is far stranger than a simple yes or no. We discovered that time as we know it probably isn't a fundamental part of our universe. Instead, it seems to be an emergent phenomenon, a very convincing illusion. We've seen how our most powerful theories, like the Wheeler-DeWitt equation, point to a universe that is fundamentally static and timeless. We've learned from thinkers like Julian Barber that our experience of time might just be our consciousness tracing a path through an infinite landscape of static nows, connecting the dots to make a story. We've explored how that story gets written by the physics of entanglement and decoherence, the quantum processes that link our internal clocks to the cosmos and create the irreversible arrow of time we all feel. Getting near the boundary where this process breaks down wouldn't just slow time, it would stretch our very perception, turning moments into eternities before dissolving the flow altogether. And from that boundary, we'd gaze upon a frozen cosmos, a perfect still life where cause and effect are suspended and the universe reveals itself as a single, complete photograph, filled with records of a past that never truly flowed. But the final, crucial realization is that we aren't just passive tourists here. We are the architects of the very phenomenon we're trying to understand. The universe, at its most fundamental level, might be a timeless, static block of information. It's the observer, the act of measurement, the creation of a memory, the process of consciousness itself that traces a path through that block and, in doing so, brings the illusion of time to life. So, can you witness the end of time? In a way, yes. But in the ultimate paradox, to do so, you'd have to give up the very thing that allows you to witness anything at all. Your own, singular, time-bound self. The boundary at the dawn of existence isn't a destination. It's a reflection. It shows us that time was never an external river we were swept along in. It was a story we learned to tell ourselves, a dream we conjured from the timeless depths of reality. The universe waits, patiently and eternally, for an observer to look upon it and give it a history. The biggest question, then, isn't what happens at the end of time. It's what story will you choose to create with yours? Einstein versus quantum physics. The war for the true nature of time. We all feel it. Time. That relentless river carrying us from a past we can't change into a future we can't know. It's the steady rhythm of our lives, the one constant we think we can rely on. But what if that's all a lie? What if the greatest minds of the 20th century, Albert Einstein and the pioneers of quantum physics, stumbled into a war over the very nature of reality itself? A war that suggests time, as you and I know it, might not be real at all. Einstein saw time as woven into the fabric of the universe, a dimension as real as space. But the strange, shadowy world of quantum mechanics whispers that it's all just a stubborn illusion, a ghost that appears out of a deeper, timeless reality. This is the story of the ultimate scientific showdown, a conflict that still rages today in the heart of modern physics. And the answer could completely shatter your perception of everything. This is the war for time itself. The clockwork universe of a bygone era. Before we can get our heads around the revolution that tore physics apart, we have to visit the world it replaced. A world of perfect, tranquil order. For over 200 years, we thought we had the universe figured out. It was an elegant, predictable clockwork machine, designed by Sir Isaac Newton. In Newton's world, space was a fixed, unchanging, three-dimensional stage. An infinite, invisible container for every event in the cosmos. And flowing through this static stage was a universal river. Absolute time. Newton's time was a relentless, unstoppable force. It was the same for everyone, everywhere. A second on Earth was a second on Mars, a second near a star, and a second in the empty void of space. Time was the great metronome of existence, ticking forward at a constant rate, completely separate from the space it happened in. Space was the stage, and time was simply the duration of the play. And this wasn't just a pretty idea, it was unbelievably powerful. Newton's laws, built on this foundation, let us predict the celestial dance of the planets with breathtaking accuracy. They described the arc of a cannonball, the fall of an apple, the tides of the oceans. In this view, the universe was deterministic. If you knew where every particle was and how it was moving at one moment, you could, in theory, calculate the entire future and reconstruct the entire past. The cosmos was a grand, predictable machine. Comforting, right? But as the 19th century bled into the 20th, tiny cracks started to show in this perfect facade. Puzzles about light and electromagnetism just wouldn't fit. The work of Scottish physicist James Clerk Maxwell unified electricity and magnetism, but his equations made a startling prediction. The speed of light in a vacuum is a constant. It doesn't matter how fast you're moving toward or away from a light beam. You'll always measure its speed to be the exact same. This flew directly in the face of Newton's physics. In Newton's world, speeds are supposed to add up. But light refused to play by those rules. This single, stubborn fact would become the loose thread that a young patent clerk would pull, unraveling the entire Newtonian tapestry. The age of certainty was ending. The first shot in the war for reality was about to be fired. Einstein's revolution. Time becomes personal. In 1905, while working as a patent examiner in Bern, Switzerland, a young Albert Einstein published a series of papers that would change everything. This is often called his annus mirabilis, or miracle year. One of these papers introduced the world to special relativity, and it started by taking Maxwell's strange prediction about light seriously. What if, Einstein wondered, the speed of light really is constant for everyone? What would the universe have to look like for that to be true? The consequences were nothing short of reality bending. For the speed of light to be a universal constant, something else had to give. That something was Newton's absolute time and space. Einstein showed that time and space are, in fact, relative. They aren't fixed. They're malleable, stretching and shrinking depending on your motion. This was a radical break from all common sense. He explained it with his famous thought experiments. Imagine you're standing on a train platform as a train speeds by. If lightning strikes both ends of the train at the same time, you, standing in the middle, will see both flashes simultaneously. But what about someone sitting in the exact middle of the moving train? From their point of view, the light from the front flash is traveling toward them, while the light from the back flash is chasing them. Since the speed of light is always constant, the front flash reaches them first. So, the person on the train concludes the strikes were not simultaneous. Two observers, two different realities. Who's right? Einstein's brilliant insight was that they both are. Simultaneity isn't absolute, it's relative. And if we can't even agree on whether two things happen at the same time, then we can no longer agree on the passage of time itself. This leads to the bizarre and now proven phenomenon of time dilation. For a moving observer, time literally slows down. An astronaut on a fast-moving spaceship ages more slowly than their twin on Earth. The effect is tiny at everyday speeds, but as you get close to the speed of light, it becomes dramatic. Time was no longer a universal clock, it was a personal, elastic thing. But Einstein wasn't done. He realized that if space and time are relative, they must be connected. He wove them together into a single, four-dimensional entity, spacetime. Space is the three dimensions we know: length, width, and height. Time, he said, is the fourth dimension. You can't move through space without also moving through time. For 10 years, Einstein wrestled with a lingering problem. This all worked for steady motion, but what about acceleration? Or, more importantly, gravity? In 1915, he unveiled his masterpiece, the theory of general relativity. In it, he gave us a completely new picture of gravity. Gravity, Einstein declared, is not a force pulling things together. Gravity is the curvature of the space-time fabric itself. Think of it like a bowling ball on a trampoline. The heavy ball makes a deep dent in the fabric. Now, if you roll a marble nearby, it's not pulled toward the bowling ball by some mysterious force. It's just following the curve in the trampoline. That's gravity. Massive objects like stars warp the space-time around them, and other objects simply move along these curves. Even light has to follow these contours, which is why gravity can bend the path of starlight. In this new picture, time got even weirder. Since gravity is the curvature of space-time, and time is part of space-time, gravity also messes with the flow of time. The stronger the gravity, the more space-time is warped, and the slower time passes. A clock at sea level ticks just a tiny bit slower than a clock on a mountaintop. Near a black hole, time would slow to a near standstill. Time wasn't just personal, its flow depended on everything else in the universe. With general relativity, Einstein had painted this breathtaking new vision of the cosmos. But while he was revolutionizing our picture of the very large, another, even stranger revolution was brewing in the world of the very small. And it would declare war on the very foundations of his new reality. The quantum upheaval. Reality dissolves into probability. While Einstein was building his smooth, geometric universe, other physicists were exploring a bewildering new territory, the subatomic world. And what they found there wasn't an elegant, predictable dance, but a realm of chaos, uncertainty, and ghostly weirdness that broke all the rules. This was the birth of quantum mechanics. It all started with light. While Einstein himself had shown light could act like a particle, photon, other experiments, like the famous double-slit experiment, showed it also behaved like a wave. When you shine a light beam through two narrow slits, it creates an interference pattern on a screen, a series of bright and dark bands that can only happen if waves pass through both slits at once and interfere with each other. But the real weirdness started when they tried sending photons through one at a time. Logic says each photon has to go through either the left slit or the right slit, right? Over time, you should just get two bright bands. But that's not what happened. Even sent one by one, the photons slowly built up that same interference pattern, as if each individual photon somehow went through both slits at once and interfered with itself. This wave-particle duality was the first sign that the quantum world doesn't play by our rules. Something could be a particle and a wave at the same time, its nature depending on how you look at it. This led to a core concept of quantum mechanics: superposition. Before you measure it, a quantum particle doesn't have a single, definite state. It exists in a cloud of all possible states at once. The photon really is in a superposition of going through the left slit and the right slit. An electron doesn't have a precise location. It exists as a wave of probability. It's everywhere and nowhere until the moment you look. The act of measurement forces the particle to choose one of its many possibilities. The probability wave collapses into a single, definite outcome. Before that, we can only talk about the odds. This probabilistic nature was a direct assault on the deterministic universe of classical physics. Einstein hated it. His famous declaration, "God does not play dice with the universe," was a direct shot at this fundamental randomness his colleagues were suggesting. He was convinced there had to be some hidden information, that quantum mechanics was just an incomplete theory. But its proponents, led by the Danish physicist Niels Bohr, embraced the weirdness. In what became the Copenhagen interpretation, they argued this wasn't incompleteness, it was a fundamental feature of reality. A particle simply doesn't have a definite position before it's measured. The fuzzy, probabilistic quantum world is the real reality. And in this new quantum framework, time played a much different, much more humble role. In the core equations of quantum mechanics, time isn't a dynamic, bendable dimension like in relativity. Instead, it's treated more like Newton's time. A universal, absolute clock ticking away in the background, setting the stage for quantum probabilities to evolve. It's a reference, not a player. At their most fundamental level, the laws of quantum mechanics don't seem to have a preference for forwards or backwards in time. The arrow of time seems to vanish. This created a deep, troubling chasm. On one side, Einstein's general relativity described a smooth, deterministic universe where spacetime is a dynamic fabric. On the other, quantum mechanics described a fuzzy, probabilistic world playing out against a fixed background of time. Both theories were incredibly successful. Yet their descriptions of reality, and especially of time, were completely incompatible. The Great Debate. A battle for the soul of reality. This conflict wasn't just some abstract disagreement, it was a passionate, philosophical battle, personified by the two giants of physics, Albert Einstein and Niels Bohr. Their famous debates were a clash over the very soul of reality. Einstein, the realist, clung to the idea of an objective universe that exists whether we look at it or not. Bohr argued that the quantum world was intrinsically fuzzy and that our observations play a role in creating the reality we see. Einstein kept coming up with brilliant thought experiments to poke holes in quantum theory, trying to find a way to measure a particle's properties without disturbing it, proving they were real all along. And time after time, Bohr and his protege Werner Heisenberg would work all night, find the flaw in Einstein's logic, and show how quantum uncertainty always won. The showdown came in 1935, with a paper from Einstein and his colleagues Boris Podolsky and Nathan Rosen. The EPR paradox, as it's known, presented their deepest challenge yet, focusing on a phenomenon Einstein would later mock as spooky action at a distance, quantum entanglement. Entanglement is one of the strangest predictions of quantum theory. It's when two particles become linked so their fates are intertwined, no matter how far apart they are. For example, you can create two photons so that if you measure one and find its polarization is vertical, you instantly know the other one is horizontal. According to quantum mechanics, before you measure, neither photon has a definite polarization. But the moment you measure one, the state of the other, even if it's light years away, is instantly determined. This is what Einstein found so spooky. The instantaneous correlation seemed to mock his theory of relativity, which established the speed of light as the ultimate speed limit for any signal in the universe. It doesn't let you send a message faster than light, but it reveals a bizarre, instantaneous connection that seems to operate outside our normal rules of space. To Einstein, this was nonsense. The only logical explanation, he argued, was that the particles had definite polarizations from the start. The information was always there, just hidden. This idea is called local realism. For decades, this was just a philosophical debate. There was no way to test it. That changed in the 1960s when Irish physicist John Bell came up with a mathematical theorem. Bell's theorem showed that if Einstein's local realism was right, the correlations between entangled particles could only be so strong. But if quantum mechanics was right, the correlations would be stronger, violating Bell's limit. For the first time, the debate between Einstein and Bohr could be settled in a lab. Starting in the 1970s, experiments were run. The results have been resounding and unambiguous. Every single time, the predictions of quantum mechanics have been proven right, and Einstein's local realism has been proven wrong. Einstein, for all his genius, was mistaken. The universe really is that spooky. Entanglement is real, and the connection between particles is instantaneous, suggesting a deeper layer of reality where our ideas of space and time might not apply. The war was far from over. It had just entered a new, even more perplexing phase. The war for the nature of time, dimension or illusion. With entanglement experimentally confirmed, the core conflict could no longer be ignored. Physics gave two totally different answers to the question. What is time? For Einstein, the answer was clear. Time is a dimension, woven into the fabric of the cosmos. This leads to a concept called the block universe. In this model, all of time past, present, and future exists at once. The entire timeline of the universe is a static, four-dimensional block of spacetime. The flow of time we feel is just a subjective illusion, like a spotlight moving along a pre-existing movie reel. The future is already there, just as the past is still there. Time is a landscape our consciousness is just traveling through. Quantum mechanics, however, paints a radically different picture, treating time as an external clock. This clash becomes a full-blown crisis when trying to unite the two into a single theory of quantum gravity, a theory for places like the center of a black hole or the Big Bang, where both gravity and quantum effects are hugely important. In the search to solve this problem of time, many physicists have come to a shocking conclusion. Maybe it's Einstein's view that's the illusion. Maybe time isn't fundamental at all, but is instead an asterisk emergent phenomenon. Just like wetness is an emergent property of a huge collection of H2O molecules, a single molecule isn't wet. Maybe time itself emerges from a deeper, timeless quantum reality. One of the most mind-bending ideas is the Page-Wouters mechanism, proposed in 1983. Don Page and William Wouters suggested time could emerge from entanglement itself. They imagined a static, timeless quantum universe. If this universe is entangled, then an observer inside it would see time passing as the state of their surroundings evolves relative to the state of their clock. Time, in this view, is born from the correlations between different parts of the universe. To an outside observer looking at the whole timeless universe, nothing would be happening at all. An even more radical idea comes from the British physicist Julian Barbour. He argues that time, flat out, does not exist at all. His theory proposes the universe as just a vast, infinite collection of nows. Each now is a static, frozen frame of everything in the universe. There is no past and no future, only an immense landscape of these possible nows. What we feel as the flow of time is just our brain stringing together a sequence of these static frames. Our experience of a past is simply because our current, now, contains records, memories, fossils, starlight that are consistent with the history. In Barbour's view, the universe is a static sculpture, and our consciousness is tricked into seeing it as a movie. This idea that time isn't fundamental is a cornerstone of several approaches to quantum gravity, like loop quantum gravity, where spacetime itself is thought to be made of discrete atoms of space and time. At this fundamental level, the concepts of space and time dissolve into a network of quantum relationships. This war has huge implications. If Einstein's block universe is right, the future is as fixed as the past, which challenges our ideas of free will. If time is emergent, as many now suspect, then the flowing river we experience is a trick of quantum entanglement. At the deepest level, there may be no flow, no past, no present, no future. Just a static, timeless quantum state. The unfinished war and conclusion. The battle between Einstein's geometric time and the timeless, quantum world continues to define the frontier of physics. The ultimate prize is a theory of everything, a single framework that can finally tell us what reality and time are truly made of. One of the leading contenders is string theory. It proposes everything is made of unimaginably small, vibrating strings. Different vibrations give us different particles. String theory needs more dimensions than the 4 we see, usually 10 or 11, which are thought to be curled up too small for us to notice. And its deeper concepts suggest that spacetime itself might not be fundamental, but just a convenient description. A competing approach, loop quantum gravity, starts by quantizing spacetime itself, describing space as a granular network of interwoven loops. In this view, time doesn't flow, it ticks. Below these ticks, time ceases to exist. In recent years, a mind-bending new idea has emerged, known as the equals EPR conjecture. It suggests a shocking link between Einstein's wormholes, and quantum entanglement, EPR, proposing that any two entangled particles are secretly connected by a microscopic wormhole. This would mean that the very geometry of spacetime is built from the spooky quantum threads that Einstein so disliked. It could be the bridge that finally unites the two warring theories. And yet, other ideas are pulling in a completely different direction. Assembly theory, a newer proposal, argues that time is very real, physical, and fundamental. It suggests that complex things, like a living cell, can't just pop into existence. They require a history, a sequence of assembly steps. In this view, time is what allows complexity and life to exist at all. So, after all this, we're left standing at a cosmic crossroads. The war for the true nature of time is not over. Was Einstein right? Is time a real dimension in a static block universe, with our sense of its flow just an illusion? Or was the quantum intuition closer to the truth? Is time itself the grand illusion, a ghost born from a timeless quantum realm? The answer remains one of the greatest unsolved mysteries in science. Reconciling these two views will require a new revolution, a new idea as profound as those of Einstein and Bohr. It will force us to question the very bedrock of our experience. The clock is ticking. Or perhaps it isn't. And the search for that final answer continues. Exploring the universe's biggest questions is what we do here. If you found yourself questioning the seconds ticking by, and you want to continue this journey into the deepest mysteries of physics and reality, make sure to subscribe and join us for our next exploration.